And further, we also created a new glacier region because we wanted to have more freedom in our melt ice runoff settings, so to say. So that is the red box over here that is covering high mountain Asia. And the melt and ice runoff settings are the same over there as in Greenland or in Antarctica. And further, we apply a virtual elevation class scheme with 36 elevation classes. And we decided to lower the maximum snow depth back to the default value because 1 meter actually, was at that time considered to be a better value for high mountain Asia instead of the 10 meter. Then some results, first results. I mainly compared my results with either observation reanalysis based data sets or satellite derived data sets. For the 2 meter temperature, I compared it with the watch forcing data era interim data set, which is considered to be one of the better data sets over high mountain Asia in terms of temperature and precipitation. I compared it, so in this figure, there is the bias distribution compared to the reanalysis observation-based data sets. And we found out that there's a warm bias over the Eastern Tibetan Plateau and China, which is region number 4, the gray region over here. And we found out also that the warm bias becomes smaller with an increasing resolution. So in that perspective, the high mountain Asia grid is doing better. Further, there are cold biases over the Western Tibetan Plateau, that is region number 1. And I think also to some extent region number 3, although we cannot see that really in the results. These become larger for higher resolution grids. Further, as a side remark, I have to mention that data sets like this are depending on the observations which are very lacking, of course, in these kind of mountain terrains. So it could be that there's some overestimation of temperature in the data set itself. Then the rainfall, snowfall. For rainfall, we can mainly see that in the monsoon-dominated regions that there's an overestimation, especially in region 1 and 2, which are monsoon-dominated. And they are the largest for the NA 120, which is the 1/4 degree model, followed by the NA 30, which is the 1 degree model, and high mountain Asia grid. The snowfall is mainly overestimated in the westerly dominated regions, where the bulk of the precipitation occurs during wintertime. And they are mainly larger for the high mountain Asia grid, followed by the 1 degree and 1/4 degree grid, and probably linked to the cold bias that is there. Snow cover and snow depth. For snow cover, it was difficult to compare it with satellite derived data set over this period. There is one, but it's not really accurate. So I decided to use MODIS as a comparison, and then only compare the first year of the 10 years of the MODIS dataset with the last 10 years of my results. And I found out that there's an overestimation of snow cover, especially during the winter time, and some underestimation of snow cover during the summertime. Although I have to mention it looks better for the high mountain Asia grid than for the other two, and that the autumn snow cover shows the best match in general with the satellite-based observations. Then the snow depth. The snow depth is slightly overestimated. Eventually, it is difficult to select a reanalysis-based dataset for high mountain Asia, but based on a paper I found out that JRA 55 shows the best of good performance compared to station-based observations and satellite-based products. So I compared it with JRA 55, and based on that, I found that it's mainly overestimated in region number 1. and it's likely attributable to the cold bias over there. Then the specific surface mass balance, where it's all about. I think you cannot read all the values here, but there's the annual rainfall plot. I think the scale is not that good, but in the southernmost part of high mountain Asia, values reach up to 5-meter water equivalent. The snowfall is also highest in the southern part, with values of over 2 meters water equivalent on annual basis. But then the runoff is especially high in the southeastern part, and then the annual ground evaporation. And if you calculate it, then eventually you end up with a negative surface mass balance. However, there are some regions, as is shown in the lower plot, especially in the southernmost parts, there are some regions where a positive surface mass balance is simulated.
2 minutes.
Yeah, is there someone? Okay. But yeah, then if I compare it with so to say area-weighted annual mass balance, which are observation-based by Semp et al. For the 3 Randolph Glacier inventory regions, then I found out that the surface mass balance in the model is really underestimated. Yes, there are some grid cells where where glaciers are growing. That's a good thing, but it means that there are still things we have to find out why that is. Now, that could probably be related to the bare ice albedo. In some figures, I found out it is rather low, actually too low, to my opinion. And the other probably factor could be related to the snow cap that is used, which is also probably too low in our region. Now, then that is eventually what we want to find out with some sensitivity experiments later on. But first to the conclusions. The high mountain Asia grid shows temperature and both precipitation biases relative to the watch forcing data area interim data set, but also shows improvements compared to the other 2 grids. It is able to simulate positive surface mass balance, where a global 1/4 degree grid is considered not able to do that because it cannot reach the snow cap. Further, the surface mass balance is underestimated compared to observation-based glaciological geodetic mass balances, which is either related to the high amount of snow, ice melt, and that again related to the low bare ice albedo, or the low amount of refreezing, which can be related to the low snow cap we have in the model. The snow depth itself and the cover are slightly improved, but it's also slightly overestimated relative to JR55. But that's of course a difficult, I cannot really make a conclusion out of that because we also don't really know about the performance of JRA55. As I already mentioned, the outlooks, there are some sensitivity experiments we need to do to see which parameters are really sensitive in terms of the surface mass balance, so we can eventually end up with a surface mass balance that is in the range of what is observed. And eventually after that, we have to rerun it again. And then we also plan it to run the high mountain Asia grid in the near future. That was my presentation. Thank you.
Thank you, Rene. We have some comments in the chat. Adam Harrington is saying that a quick aside to the group, the HMA qubit timings of 85 to 90,000 core hours per simulated years are inflated by 10 to 15,000 core hours due to the increasing elevation classes from 10 to 36. René, a question from you. Is a precipitation comparison, is it from era interim?
It is based on era interim. So what they did in watch forcing data era interim dataset, they applied the so-called watch forcing data methodology. So they included, for example, lapse rates to downscale the temperature, and the precipitation has been bias corrected based on the stations of the GPCC. So yeah, technically it is based on the era interim, but not directly related to era interim.
And there was a question from Heiko Goltzer. How does interannual and interdecadal variability look like in this region? Is it wise to compare a 10-year period? Is it wise to compare a 10-year period to observation? And can you find another period that better matches observation?
I think in here it is a bit difficult to, we only have 20 years of data, and we are looking at a difficult period. Actually, the most, for example, the most satellite-based observations are from 2000 and afterwards. That is also the time that the research and observation really start to rise from the ground in this area. So especially before that time, it's quite difficult to match in general, and especially because we are looking from the 1980s and 1990s. I also prefer to compare it with data that is also over this period. Because otherwise you have some different climatology, for example. Yeah.
Thanks. So in the interest of time, we're going to have to move on. There are several additional questions for you. And I would say you can ask a question during the break, or maybe René can answer them on the chat. We'll be saving the chat that we can send you later on.
Yeah, okay. I will try to answer them, but I will also things go to sleep soon. Yeah. Okay.
But otherwise, you can take the conversation offline for the time being. Our next speaker, is going to be Miren Biscayno from Delft University, and she's going to talk to us about timing thresholds and processes for complete future Greenland deglaciation. Miren, the floor is yours.
Yeah, thank you. I hope you can hear me, and that I can start from the beginning as well. Okay, and that's better. Okay, so this is about the future of Greenland, and we are thinking very long term, and we are thinking very aggressive. We are gonna have a look here to a simulation that is coupled with the community air system model and the community ice model under 4 times CO2 forcing. It is a scenario of increase of 1% per year, and the stabilization is at year 140. And then we continue running. Well, the motivation for this is that Greenland is giving us very bad news. Recently, that we have a new record mass loss in 2019 after the previous record in 2012. So more than 1 millimeter per year in both years of sea level rise, only from the Greenland ice sheet. Okay, so the question is, how could Greenland evolve if we are very aggressively emitting, and so how would the future be? How fast would things be? Other people have been busy with this question. For instance, we have here a couple of examples from coupled global climate and ice modeling. The first one is from 2005 from Jeff Ridley. He estimated 3,000 years. And as the ice sheet is deglaciate, is retreating, it splits into parts. So here there is a part in the south, and then the main body here, and the retreat continues, and the ice sheet somehow survives in the areas with high elevation bedrock. 3,000 years. Here, Gregory et al. In 2020, they do this study with a coarse resolution climate model. It is famous. This is the name. So under abrupt 4 times CO2, it takes 9,000 years. But when it is uncoupled, it is much faster, 3,000 years. Here we have another study from Alexander Robinson. Here, for an 8 degrees global warming, it is about 2,000, a little bit more than 2,000 years to get rid of the poor ice sheet. And then we have also a recent study where it is about ice sheet modeling, PISM, sorry, and everything goes very fast. No? So I'm gonna go very, very fast here, and yeah, the ice sheet is lost after only 1,000 years. Okay, so here we use the coupled model. To my understanding, this is the most advanced simulation that is coupled. So, and I'm saying advanced because of 4 points at the same time. The first one is that we have coupling of ice dynamics, SMB, and climate. Second, that the SMB simulation is advanced with a very advanced simulation of the processes in CLM. And there's no processes, I mean, and very strict coupling with the atmosphere. Advanced ice flow simulation with a higher order approximation, and this is advanced for a couple simulation. So it is not top of advanced for ice sheet modeling only, but most of couple studies are done with shallow ice approximation. And finally, the resolution is unprecedented for a combination of ice sheet modeling and climate modeling. So the climate resolution is the standard of IPCC simulations for CESM, so 1 degree, and the resolution of the ice sheet model is 4 kilometers. Now, so we are simulating processes of SMB at the sub-daily time scale. We have coupling with the ocean, so ice sheet model is providing freshwater fluxes, and runoff is provided directly from CLM to the ocean. No forcing from the ocean is given to the ice sheet, though. The topography is updated in CAM every between 5 and 25 years. And in this long simulation, we have at some point to save computer time, and we do it from the climate model from the year 500, because most of the climate change has taken place in the first 5 centuries. Then we go with a 1 to 5 coupling. So the ice sheet model is forced with every 5 years, so for 5 years with output from the climate model. Okay, so here we have a video where we can see the evolution of surface velocities. So the top of the range is 1,000 meters. So you can see how the ice sheet has retreated by more than 30% of the area by now. So we are starting with overestimation of volume of 1 meter sea level equivalent, and the area is also overestimated. By year 350, 20% of the ice sheet area is lost. And the first part of the simulation up to year 350 has been already published in James in 2020. The first author is Laura Mungefer. So as we continue with the simulation, we can see that the first part to be lost is the southern part of Greenland. There is no splitting into ice bodies, mostly. No splitting, and what is being left here is an ice cap in the northern part, not too far from the current summit to today. Okay, so we are losing it, and we are close to the end. So you can start guessing. Okay, so it's less than 1700 years. Okay, so this is the climate simulation. So please follow the blue line. So by year 500, we have a warming of 9 Kelvin, and it is by 1700 10 Kelvin. But mind that this between year 500 and the end, the rate of warming is 1/5 of what it should be, because we are coupling only every 5 years. Okay. Now here you have time series of the main variables of interest, the volume, the area, the sea level rise, and here the components of the mass balance. So here you can see rates of deglaciation. Maximum deglaciation rates are between year 400 and 600 approximately, but as the ice is losing mass, then obviously there has to be a maximum contribution to sea level rise that is related to how much mass is left. So from here, from year 700, more or less, when the ice sheet has 50% of the original size, the glaciation rates decrease. The yellow line here is the SMB. It becomes negative by year 120. This other line is obviously the mass balance, or this sea level rise contribution, and first is at 0, so the ice sheet is in equilibrium at the beginning. The ice sheet becomes terrestrial more or less by year 300. No? So the ice discharge, which is this green line, is more or less 0 by that time. So. Here you have the dynamical evolution that you have seen before. So these are the surface velocities corresponding to 75% area, 50% and less, and 25%. And you can see how the maximum velocities are being simulated as the ice sheet is retreating in the areas with maximum slope. You can also see it here. So this is a transect west-east. You can see here where the transect is, and you can notice how the base reaches melt conditions in the areas that have a high slope for the topography. So this is where you have these red parts. And a funny effect that you can see for the internal temperatures is that the upper layers become colder with global warming. And this is because we have reduced refreezing as the ablation areas are expanding. So we don't count from the heat that is released from refreezing. Okay. This is the evolution of the SMB. We are starting with ablation areas that take more or less 8%, so below 10% of the total surface of the ice sheet. And from year 120, there is an acceleration. So the equilibrium line altitude is rising substantially, and there is a very quick expansion of the ablation areas. By now, year 400, yes, the ice sheet is ablating in more than 50% of the surface. Okay, so this is how it goes. Okay, so if we are looking to components, so what we see is, so this is in gigatons per year, but we are going to consider the area change. And if we follow the kilograms per square meter and year, what we can see clearly is that the snowfall is not reducing much or is not going down in the first centuries, but eventually it goes down. And this is because the elevation is going down a lot on top of the global warming, and the rain fraction is increasing very much. The melt accelerates very much in this period, and also at the end when the mean elevation is very low. And refreezing is increasing at the beginning up to year 120, 140, and then decreases. And this is because of the warming, so that the refreezing capacity is compromised, and the ablation areas are expanding a lot. Regarding energy, at first, most of the energy is supplied by increased long wave radiation, but then the albedo kicks in, the albedo feedback, and is short wave the main contributor to the melt energy, and also the turbulent fluxes are increasing very much during the simulation. We can compare with a simulation with fixed topography. And what we see is that for half size, if we are comparing the climate, so the climate change is, the global change is the same in both simulations, but the ice sheet is not changing. And for half size, we see much warming in the areas that have deglaciated. And when the ice sheet is gone, we see temperature differences of close to 20 degrees because the ice sheet is gone. No? So the ice sheet really cools down because it has a high elevation, among other things. Okay, so the conclusion here is that under this very high forcing, and in a climate model that has a high equilibrium climate sensitivity, the ice sheet is lost over less than 2 millennia. But yeah, we have to remember this is very high forcing, and the model has a very high climate sensitivity. The maximum deglaciation rates take place for a warming of 9 Kelvin and 25 to 35% Greenland ice sheet volume reduction. And we see a retreat that is faster in the southwest margin than it is for other margins. The northern basin also retreats relatively fast, and these two basins are somehow slower. The very, very slow one is, of course, this one that is retreating in a way that doesn't make the ice sheet split in two parts, as we have seen for other studies. And yeah.
Thank you, Miren.
I think I leave it here.
That sounds great. While we switch speakers, we have time for one question.
I have a question. So I'm wondering how much, so this is a very fast deglaciation. You know, I remember that 15 years ago that Ridley paper did a similar experiment, and it was, you know, on the order of 4,000 years to deglaciate Greenland. So I'm wondering how much of this might be due to the very high climate sensitivity of CAM 6. I don't know if you have any insight, if you've looked at how this operates in CAM 5, but could you comment on that?
Yeah, we didn't. Yes. So of course the climate sensitivity is playing a role here. Yeah.
Oh.
But there are many other differences with the study of Ridley et al. So differences in resolution, shallow ice approximation for the icing model. Calculation is based on PDDs in that case, so degree days and many others.
Right. I can imagine it's very hard to compare to that study. But yeah, I think, you know, the CAM6 climate sensitivity is a little worrying on how high it is. And so
Yes.
I was just wondering if you've done any similar experiments with CAM5. I know these are really expensive, so I doubt you have, but have you looked at CAM5 deglaciation timescales?
No, and I wonder whether this could be done. But anyway, the main focus here is not whether it is 1700 or 3000 years, but it is why and how it is happening. So it is of course interesting as a next step to explore less extreme scenarios that are not 4 times CO2 and see how things go. And also there is a follow-up presentation now that is looking at different levels of forcing and how the ice sheet goes. Yeah.
All right, thank
but
you.
Yeah, it's a caveat of this estimate that the climate sensitivity is very high. Yes.
Thank you. So we need to move on. Can you stop sharing your screen, Miren, please? And our next speaker is Michel Petrini from the University of Ghent as well. And he's going to talk about the multi-millennial response of the Greenland ice sheet to anthropogenic warming.
Hi.
And you can start sharing your screen whenever you want.
Okay, that's perfect. Okay, that's all right. Share. Just a second, I need to allow sharing.
You can't share your screen?
No, not now, but just a second. Okay. Now it should work. Just a second. Yeah, perfect. Yeah, all right.
There we go.
You should be able to see it now. Okay, perfect. So also this study results from the collaboration between TU Delft and NCAR, with the additional contribution of Maaike Scherenberg, who is now a PhD student at Utrecht University. And so here we will look at the multimillennial response of Greenland, simulated with the community ice sheet model, and in response to different global warming level. So I will just quickly introduce the aim of the study and show some previous results. Then I will explain briefly how a specific setting of the community Earth system model to force CESM with elevation varying surface mass balance, something called the T-COMSET in the CLM technical notes. I will just illustrate the setup of our simulations, and then I will just show and analyze the results. So first of all, we want to investigate the long-term stability of the Greenland ice sheet, and we have a few questions. First of all, are there thresholds in global mean temperature or SMB beyond which the ice sheet largely retreats or disappears? And if there are sectors of the ice sheet that are more vulnerable to a decrease in surface mass balance, what are the timing of the retreat depending on the warming levels? And also what are the equilibrium states of the ice sheet in response to these warming levels? We know that early, relatively recent study found a threshold in global mean temperature between 0.8 and 3.2 Kelvin with intermediate equilibrium states in Robinson et al. 2012. Then a later study by Leverman et al. 2013 found a slightly lower threshold, 0.8, 2.2, with an abrupt transition between stable Greenland ice sheet and ice-free Greenland. And in the latest study by Gregory et al. 2020, for global mean temperature forcings larger than 3 Kelvin, the ice sheet is mostly lost. But again, there is a wide range of equilibrium states for lower forcing. There is a paper by Frank Paten et al. 2018 showing that the northwestern sector of the ice sheet is sensitive to SMB changes, where the northwestern is this sector here in green, which is a bit different from the INB basin that we know today. Anyway, as for the timing of the deglaciation, we have times ranging between 1 and 3,000 years for very high forcing, 8,000–10,000 years for, we can say, medium forcing, although it's a bit different to compare between the study because they use, of course, different methods, and 20,000 years or more for lower global mean temperature anomalies. Now, in an ideal world, of course, we would, to answer this question, we would run multiple fully coupled multi-millennia CESM simulations, but of course, this is unfeasible computationally. There is the existing simulation, the coupled 350 years long 4 times CO2 CESM season simulation of the Greenland ice sheet, published by Montievert et al. 2020. This is basically the first 350 years of what Miren Biscayno just showed. This idealized greenhouse gases scenario with increase of 1% CO2 until the 4-time PI level is reached. And in this run, we do have GMT global mean temperature increased by 8.2 Kelvin with respect to PI over 350 years. And the simulated, this is even more important for our study, the simulated SMB over the Greenland ice sheet is saved in annual Kepler history files, and I will show in the next slide. We then run multiple CESM run within the CESM architecture, cycling different SMB intervals from the 4 times CO2 CESM run, where each interval will correspond to a different global warming level. Now, the method that we use to force CESM, what we have is that in a CESM run, the atmospheric surface temperature and specific humidity are downscaled from the CAM6 mean grid cell elevation to 10 different elevation classes using a lapse rate of 6 Kelvin per kilometer. And at each elevation class, the precipitation is then partitioned into rain versus snow, depending with a linear ramp scheme based on the surface temperature. And then precipitation and temperature are used to calculate with a surface energy balance scheme the surface mass balance, given as snowfall plus refreezing minus snow melt minus ice melt minus sublimation. The SMB is at each elevation class is then downscaled by the Kepler into the CESM high resolution grid. And as I said before, the SMB at each elevation class is saved in these annual Kepler history files during a CESM run. So the CESM architecture allows to force CESM by cycling these existing Kepler history files containing information to downscale the SMB forcing at different elevation. So while the ice sheet evolves in CESM under this specific setting, the SMB will change according to changes in surface elevation. And in this way, we can account for the surface elevation feedback. Now, what basically we did to set up our runs, this is a time series for CO2 forcing, global mean temperature, and surface mass balance of the coupled CESM 4 times CO2 simulation. And we select different time intervals corresponding to different warming level. You can see the color band here. So we select levels corresponding to +1 Kelvin, +2 Kelvin, 2.8, 3.6, 5.2, and then a last very high forcing 8.5 Kelvin. And then we will cycle the SMB from each interval until either the Greenland deglaciation or stabilization. Now, I just want to show you the SMB. So you can see a map of the SMB for the PI control here. This is the 1.5 CO2, so +1 Kelvin. And this is the 2 times CO2, +2 Kelvin. You can see SMB and the anomaly. And you can see that for these two scenarios, the total SMB is largely positive and the equilibrium altitude, the LA, is mostly unchanged. And the ablation is slightly higher at the western margin, but not much. And while the accumulation is slightly lower in the southeast for the 2 Kelvin scenario. Now, if we look at the +2.8 Kelvin and +3.6 Kelvin, for the 2.8 case, we can see that the SMB is still positive. There are some small ELA changes in the southwest, northeast basins. We do have an ablation that is starting to get higher in the southwestern and central western margins, and the accumulation is still lower in the southeast. For the 3.6 Kelvin case, the total SMB is still positive, but is less than 50% of the PI case, and the equilibrium line altitude migrates in the western north and northeastern basins, we do have higher ablation at the margins and accumulation actually that is still close to the plus 2.8 Kelvin case. These are the last two high forcing, plus 5.2 and plus 8.5. And in this case, the total SMB becomes negative, largely negative for the 8.5 Kelvin. We have a stronger ELA migration and the ablation gets much higher. And also for the 8.5 Kelvin, you can see that also the accumulation pattern changes. Now, I will just show you our results here. You can see, first of all, a time series of Greenland ice sheet volume and area for the different runs. We have in blue, dark blue is the +1 and light blue is the +2 Kelvin. It's a bit hard to distinguish, but you can see them here, for instance. Then the green is +2.8, the yellow is +3.6, light red +5.2, and dark red is +8.5. And you can see that with a forcing of a +8.5 Kelvin, the Greenland ice sheet deglaciated in around 2,000 years, so similar to the coupled run that Miren showed before. And the SMB got as low as -7 millimeter, 7.5 millimeter per year, and you can see that here. And I will now take out the high forcing from the plot just because it's easier to look at the other runs. For the 5.2 Kelvin, we see that the Greenland ice sheet almost fully disappear. And we will see maps later to show that only few ice caps remains. And the timing is about 5,000 years. And the SMB reached a minimum of -3 millimeter per year in 2,000 years. For the +3.6 Kelvin case, the Greenland ice sheet does not fully deglaciate. However, after 23,000 years, the volume loss is quite high, 7 meter sea level equivalent, which is 85% of our PI initial volume, which is a bit overestimated. We do see, though, that the 35–40% of the initial area is still remaining, still ice covered, and the SMB starts as positive and then becomes negative and remain negative for between 3 and 16,000 years. Then for the +2.8 Kelvin case, we see that the Greenland ice sheet volume and area loss is quite limited to 2 meter sea level equivalent, and also the area loss is small, 15% of the area, and the SMB remains positive throughout the run. And for the last two cases, 1 and 2 Kelvin, the Greenland ice sheet remains stable with SMB and ice discharge that are still close to PI values. This is for the 2.8 Kelvin case, a map of the final state of the ice sheet. And I will just run a video of these fields. We have ice thickness, ice thickness anomaly, SMB, the rebound, and the ice velocity. And you can see that, oops, sorry. And it's split here, but actually it will reconnect later around 20,000 years. And this is just because an increase in the rebound. So the rebound caused an increase in surface elevation, and so the ice sheet re-advance and the two main domes reconnect. And you can see also that the northern basin in the west is retreating a bit. I will just go back for a while. The northern basin is retreating in the west until around 27,000 years, but then again the margin re-advance, and also in this case we can see the signal of the rebound. And it's also interesting to note that the ice dynamics doesn't change too much throughout the run, and most of the outlet glacier in the north and eastern margin remain active. Now this is the same plot for the +3.6 forcing. And you can see that now the southwestern basin retreats faster earlier, and the Greenland ice sheet split from the south by 5,000 years. And the northwestern and northern basins start to retreat later than the southwestern, so after 5,000 years. But as they start, they leave the basins ice-free by 15,000 years. And also the central western basin retreats later, mostly after 10,000 years. And by 20,000 years, two thin separated ice bodies are left in the south and in the east. And the last two videos are for the 5.2 forcing, and you can see here how the retreat is is much faster, and by 5,000 years, the ice sheet is basically gone, and there are only few ice caps remaining in the east. And this is the same video for the very, very high forcing of 8.5 Kelvin. And you see that already after 1800 years, the ice sheet is gone. And well, I will skip this to leave time for some comments. This is just a wrap up of the results. Of course, we want to investigate better the warming interval between 2.8 and 3.6 Kelvin to find if there is an abrupt threshold or not, or there are multi-equilibrium states. And of course, also the interval between 3.6 and 5.2 is interesting. And we also need to do some uncertainty estimation. And yeah, that's it. Thank you.
Thanks, Michele. We have time for a few questions. One question from Marcus. Are the long transient simulations accounting for orbital changes?
Yeah, no, they are not. We're just running CESM, so the forcing is just what is simulated in the 4x CO2 run. So that's an actually good point. That is more than projection is finding a threshold in temperature.
Any more questions for Michele? Okay, if not, then we can move on to the next speaker. Thanks, Michele.
Thank you.
If you could stop sharing your screen, great. And our next speaker is Raymond Servold from Delft University, and he's going to talk about projecting the 21st century Greenland ice sheet surface melt using artificial neural network. So Raymond, if you're ready, you can start sharing the screen, and the floor is yours.
Yes, now I have to see. Wait. I have to share my entire desktop, that's fine. You see my screen now?
Yes.
And the mouse also, right? Wait,
Yes.
let me also get you.
Your mouse, no.
Okay, well. Yes, so I will talk about a small project I did together with Miren, which is about projecting 21st century Greenland ice sheet surface melt using artificial neural networks. So the motivation behind this study is that surface melt is currently the primary component of Greenland ice sheet mass loss. Here is a plot from Noel et al. Where you can see the melt in yellow is really going fast from the 1990s and increasing very fast. However, projections of future surface melt are scarce because there are few global climate models that can realistically simulate Greenland ice sheet surface melt. And downscaling of global climate projections through regional climate models is expensive. So then the question is how to reliably and inexpensively translate global climate projections to projections of surface melt. So in this presentation, I will evaluate the option of using artificial neural networks and make projections of 21st century surface melt using these artificial neural networks. So the neural network is set up as follows, that you have an input layer, which is a climate simulation where I take the summer averages of either near surface temperature, 500 hectopascal geopotential heights, cloud cover, incoming radiation, or snowfall. Then it is sent to this yellow part, which is the hidden layer in the neural network. And this hidden layer is a map of weights. And these maps weight the input and make a sum. And I've written down the equation. So for each of these four yellow hidden units, you calculate the weight times the input with which I have denoted as x. If this y is less than 0, it is set to 0, and if it is higher, it is forwarded as the sum to the output layer, which weights what comes out of the hidden layers and makes a melt projection. Now, in order to train these weights in the hidden layer and the output layer that creates the melt projection, I need some data, and for that I used CESM2 climate simulation and CESM2 Greenland surface melt. So then this goes into an iterative procedure where I send the CESM2 climate simulation through, and it guesses the melt projection. Luckily, I have the answer from those climate simulations, and then it updates the weights until it gets as close as possible. And the CESM2 data I use for training are 10 historical simulations, 3 SSP 1 to 2.6, 3 SSP 2 to 4.5, 10 SSP 3 and 3 SSP 5. Yeah. So for the evaluation, the first part of the evaluation, I use an independent CESM2 simulation. So a simulation from CESM2 that this network didn't see or train on. So here in the black line is the melt that was simulated by that CESM2 simulation, so explicitly calculated from the climate model. The blue line is the surface melt that is projected by the neural network. Here I'm only showing what my result was for the near surface temperature. This blue line is then the sum of the orange line and the green line, and the orange line and the green line are the melt that comes from hidden unit 1 and hidden unit 2, so one of these two hidden units. And we can see that for this variable, the network used 2 hidden units and the rest were set to 0. And we can see this neat thing with the orange line that it pre-2040, it accounts for all the melt. However, in 2040, then the hidden unit 2 is activated and rapidly increases and gives the opportunity to represent this nonlinearity in the melt evolution. So I also want to show each of these hidden units. As I said, it's a map of weights where you weight the input. So the orange line takes the near surface temperature summer average input and weights it by this. So it positively weights temperatures very strongly at the southern dome, but also close to the margins, in addition to the ocean around the western margin of the Greenland ice sheet. So for this green line that is activated later and sharply increases, the neural network weights the ocean here even more. It weights the southern dome a little bit less, but it puts a lot more weight to the temperature evolution around the summit and the interior of the Greenland ice sheet, in addition to the ocean outside of the northeastern parts because of sea ice loss and increased temperature. But all in all, the melt calculated by this neural network compares very well to what is simulated by CESM2, and of course, it probably should, since it's the same data. So I also made an evaluation against the MAR, which is a regional climate model, which simulates with high resolution around the Greenland ice sheet. So what I'm showing here is in the black line, then it's the melt calculated by MAR when using CNRM CM6 as the global climate forcing, CNRM ESM2, UK ESM1, and MRI ESM2. And then for each of the variables I used to train the network, so they are independently fed through the network. So what we can see is that not all of these variables are really able to pick up what is simulated by the regional climate model, which is probably because they don't generalize too well to data they do not know. in general, and as can be seen in this table over here, the near surface temperature and snow are those that gives the best estimate when compared to MAR. And so therefore, I only use the near surface temperature and the snowfall for making projections to make the projection as reliable as I possibly can. So when I use these two variables, then I again compare against the MAR for the same climate models. The dotted are is the MELT calculated by the neural networks, and the solid line is the MELT calculated by MAR. And as we can see, it gives a fairly good, it agrees fairly well with the MAR simulated MELT. So then I use the full CMIP6 archive of snowfall and near surface temperature and run them through the neural network. And so first we can look at the global mean near surface temperature anomaly. So I do this for the historical, for SSP1, SSP2, 3, and 5. And these are anomalies against the 1979 to 1998 climatology. And on the left side, the near surface temperature global mean anomaly and the melt anomaly for Greenland ice sheet surface melt. So for the historical period baseline, there's a 16 degree global mean temperature and 521 gigatons per year of ice sheet melt. For the SSP 1 to 2.6, the increase in the last 20 years of the simulation is 1.6 Kelvin of global mean temperature and 400, which then translates into 414 gigatons per year of increased surface melt. 2.5 degrees extra warming in the SSP 2 to 4.5 translates into 724 gigatons per year. 3.5 Kelvin global mean warming to 1,031 gigatons per year. And the most pessimistic scenario gives a global mean warming of 4.4 Kelvin and translated to 1,378 gigaton per year. And these estimates are quite high compared to what was previously estimated for the CMIP5 models. So looking into what gives the most uncertainty in this melt projection, then we can see the spread. So I take then the standard deviation for what for the differences between what the two variables project, for the internal climate variability, for the model spread, and for the scenario spread. So we can see that the model spread is the main source of uncertainty in this projection, with the scenario spread becoming increasingly important. Further, we can see that the scenario uncertainty is very, very low before 2040. So more or less the scenarios cannot be distinguished from each other until year 2040. So the conclusions are that the UNS project surface melt compares well against an independent CESM2 simulation and regional climate simulations by MAR. The end of the century surface melt increases in the range of 414 to 1,378 gigatons per year. And these projections are higher than previous estimate due to the higher climate sensitivity of the CMIP6 models, as you can see on the figure here, which gives the end of the century, so the 20 last years melt anomaly against the global mean temperature. Then you can see that the melt anomaly over Greenland gets higher for a higher global mean temperature anomaly. And the model spread is the main source of uncertainty in the projections. Yeah.
Thank you, Raymond. So we have time for a couple of questions. Either in the chat or raise your hands or unmute yourself. Heiko.
Yeah, hey Raymond, thanks for the nice presentation. I was wondering, so you make these projections for melt, but wouldn't it be interesting to do the same for runoff? Because, you know, melt is kind of like a predecessor for runoff, and you may want to project how refreezing capacity increases or decreases. Yeah.
Yes, I think that's a very good question, and absolutely. So I started this project as a last part of my PhD, and I decided to focus on the surface melt. I guess all components of the Greenland surface mass balance, in addition to the surface mass balance, could be interesting to project through such a network.
Okay, thanks.
Thank you. Any more questions for Raymond? I can't see any. So, well, thank you, Raymond, for your presentation. You could stop sharing your screen. We move on to our next speaker.
Yes.
Our next speaker will be Trevor Hildebrand from the Salamos National Lab. And he's going to talk about projection of 21st century sea level contribution from the retreat of Humboldt Glacier in North Greenland.
There.
Great. Okay, are you seeing my screen?
No.
Can you not hear me?
I can hear you, but I cannot see your screen.
You cannot see my screen. Okay. Can you see this?
Yes.
Okay, and if I go to present mode, is that still?
It's gone.
It's gone. Okay, so I guess I will stay out of present mode. Sorry, we're only allowed to use the browser version of Zoom at Los Alamos, and that has very limited functionality.
I can see your slide fine like this.
Okay. Yeah, sorry for that. So I've been working on Humboldt Glacier in North Greenland. It's outlined in this purple contour here. So on the left is the recently published map of thinning and thickening over Greenland from the ISAT and ISAT-2 missions. And so you see for North Greenland that Humboldt Glacier has the largest area of thinning of any of these northern outlet glaciers. The middle panel here is the ISMIP-6 Greenland ensemble mean thickness change over the 21st century for the Merak 5 forcing. And we see once again that Humboldt is the northern glacier with the most area of mass loss, as well as this sort of complete loss of the marine terminus here. And just as a reminder, this right-hand panel is the full ensemble from ISMIP-6 showing that we get about 2,100 plus or minus 35 millimeters of sea level out of Greenland as a whole. And so the concern is that Humboldt could be a large contributor to this over this century. So this is a Landsat image of the terminus of Humboldt Glacier. So this is ocean and sea ice here. And Humboldt is by far the widest outlet glacier in Greenland. It's about 100 kilometers or 95 kilometers across the calving front. I'm showing here terminus positions mapped from 2000 to 2017. So in the northern section of the terminus, it's retreated about 10 kilometers over these 17 years. There's nothing mapped in the southern portion of the terminus because that's stayed relatively stable. And this is particularly concerning because of the bed topography behind this retreating portion of the terminus. So everything below sea level is in gray here, and this dark gray patch is about 300 to 400 meters below sea level. So along this rough flow line, we see the 2007 glacier surface in blue, and we see that it's not yet reached this ever deepening But if we look at a series of surface speed from 2000 to 2017, we see this near tripling of surface speed at the glacier front and a 50% increase or so 20 kilometers up glacier, even though it hasn't yet retreated down this backsloping bed. So the goals of this project in the long term are to understand the retreat of Humboldt Glacier and what is the primary forcing here and what will control it in the future, and then to project the retreat and sea level contribution from Humboldt over this century. And to do that, we're using the MPAS Albany land ice, or MALI ice sheet model, which is a higher order finite element code that uses an unstructured mesh. Here we're using 1 to 10 kilometer resolution, so 1 kilometer near the glacier front and in the first few tens of kilometers behind it, and 10 kilometers resolution towards the interior, towards regional domain. And we're forcing this with RCP 8.5 climate forcings taken from ISMIP 6, and currently we're using the ocean temperatures from MIROC 5 and surface mass balance of runoff from MAR and MIROC 5. To parameterize calving and melt at the margin, we're using these two common parameterizations. So for calving, we use the von Mises stress calving law, which defines a calving rate that is some fraction of the ice velocity determined by the von Mises stress at the terminus, and some threshold stress usually taken to be 1 megapascal. Most studies just remove floating ice. We've set a low calving threshold for floating ice of 50 kilopascals. For submarine melt at the terminus, we use the ISMIP 6 parameterization that sets melt as a function of water depth, subglacial discharge, and ocean thermal forcing, and those subglacial discharge and ocean temperatures are taken from the ISMIP 6 forcings. So we begin by optimizing the basal friction field using this inverse approach. So we assume a power law form of the basal friction relationship, and then we invert for C this coefficient using an exponent of 1. So we're actually inverting for the linear basal friction law to minimize this cost function that includes both the mismatch to velocity observations and this regularization term to keep our friction coefficient smooth. So you can see in this map of the basal friction coefficient on the right, where we have a slippery bed in these dark red and black areas, corresponds to the regions of high surface velocity. And so I've run this initial condition forward from 2007 to 2018 here to look at the effect of different exponents on the velocity term in the basal friction law. So m is the denominator of that exponent. So m equals 1 being linear, m equals 20 being strongly nonlinear. And we find that for similar amounts of retreat, shown in these top panels here, we get wildly different speed up with these basal friction laws, which is no surprise. But we need this very small exponent of 1 over 20 in the basal friction law to sort of replicate that tripling of surface speed near the front. And I'll just show this compared to the observations of surface speed on the right. Here's the same model result on the left. And so we're still working on tuning the calving and melting parameterization to better match the observed amount of retreat. So we're overestimating retreat a little bit here, but this does an okay job with the default parameters, and I'm going to show results for these 4 different basal friction laws using those parameter choices. So running forward to 2100, showing here a map of bed topography. So everything in brown is below sea level. These 4 runs with the different coefficients are shown in these colored curves, the glacier terminus, and the glacier terminus at 2007 is shown in the white. So I'll step forward in 20-year increments starting in 2020. And we see there's a little bit of jostling back and forth, but by and large, this very non-linear basal friction law gives us the most retreat, and the linear basal friction law gives us the least retreat, which is, again, not surprising. But if we look at this in terms of the amount of volume lost over the century and the equivalent amount of sea level rise, we see that there's some decent spread over the first half of the century, but by the end of the century, these all agree pretty closely on about 4 millimeters of sea level rise by 2100 for all choices of basal friction law. And on the right-hand side here, I've parsed the volume change out into the individual components for the linear and the most nonlinear law. So purple is the ocean melt, green is calving, separated out into calving from grounded ice and calving from floated ice in dashed and dotted lines, and the surface mass balance is in pink, and the total mass budget is this bottom curve here. And so in both of these scenarios, what you see is that by about 2050 or 2055, surface mass balance really takes over as the dominant source of mass loss here. And this is illustrated even further by what I'll show next, which is a set of runs using these same basal friction laws, but with ocean melting and calving turned off entirely. So just surface mass balance forcing and allowing the grounding line to migrate accordingly. So that's shown in these dashed curves here. So there's a slight decrease in the amount of sea level rise by the end of the century, but it's still on the order of 4 millimeters with only surface mass balance forcing. So here you probably noticed that we're starting to get a really rapid rate of sea level rise by 2100. So I ran this forward to 2150, holding these forcings constant at 2100 because the ISMIP6 data sets do not include output past 2100. And so here is the glacier terminus positions for these 4 runs at 2150, and I'll just show the 2100 margins for comparison. So by 2150, we're getting about twice the retreat as at 2100, but in terms of sea level rise, we're getting about 11 millimeters, which is almost 3 times the amount that we get over the 21st century alone. Okay, before I wrap up, I want to just talk about a parallel project that our intern Abby Rote has been working on, which is modeling the subglacial hydrology at Humboldt Glacier. So on the left here is just a map of her model output in terms of the water flux under the glacier. And she's been working on comparing the melt rate at the glacier terminus determined using an explicit subglacial hydrology model versus using just the simple spatially uniform discharge prescribed in ISMIP6. And so here, anything in red is where her model predicts higher melt, and anything in blue is where the simple treatment in ISMIP6 predicts higher melt. And so we see that using the simple treatment, we're underestimating spatial variability, but the total budget of melt is the same to within about 5%. So we feel justified using this simple approach for now. However, a longer term goal of the subglacial hydrology work is to use the effective pressure field from the subglacial hydrology model to feed into a basal friction law that is effective pressure dependent.
2 minutes.
So that brings me to my summary. So these preliminary experiments predict about 4 millimeters of sea level rise from Humboldt by 2100 and 11 millimeters by 2150, and this holds for a wide range of basal rheologies. And just for context, the ISMIP6 ensemble predicted about 100 plus or minus 35 millimeters of sea level rise by 2100. So Humboldt Glacier in these simulations is a significant contributor to that, but not by no means dominant. We found that a very small exponent on the basal friction law is required to reproduce the observed speed up, but that choice of exponent actually has a relatively small effect on sea level rise projections this century, and that sea level rises and mass loss are really dominated by surface mass balance. And in the future, we're currently working on refining the tuning of our Cavium melt parameterizations to better match the observed retreat. We want to force this with all the available model output from ISMIP-6, and we want to incorporate this effective pressure term from subglacial hydrology modeling. So thanks.
Thanks a lot, Trevor, for your presentation. Do we have time for questions?
I suppose I'll ask one. Does the grounding line ever approach that large over deepening in any of your simulations?
So yes, but we never get fully deglazed. So the over deepening has sort of two parts. It's over deepened for about 30 kilometers or so behind the modern terminus, and then there's sort of a ridge, and there's a second over deepening. So by 2150, this first over deepening is entirely deglaciated, but the second one is only just starting to deglaciate. So that could be, yeah, maybe by 2200 in these simulations. If I run these out further, we might see a lot more change there.
Okay, thanks.
Any more questions for Trevor? No? All right, in which case, thanks, Trevor, for your presentation. And we move on to our last speaker from this morning's first half of the morning session, Chloe Wicker from University of Michigan, and she's going to talk about incorporation of bare ice capabilities into a snow radiative transfer model.
Okay, hello everyone. Can you see my screen?
Yes.
Okay, great. Thank you for the introduction, Gunther, and thank you for all the great talks this morning. They've been really interesting. So my talk today is going to be, like Gunther said, on the incorporation of bare ice capabilities into a snow radiative transfer model. So a quick overview. Our motivation is essentially the melt of the Greenland ice sheet, which we've heard a lot about this morning. So my group has developed a radiative transfer model that is able to explicitly represent snow and ice albedo. I'll go into some preliminary results of our new model and then go into the relevance of it to the CESM community. So first off, the Greenland ice sheet is currently the largest contributor to sea level rise. And in the last approximate decade, the majority of mass loss from the Greenland ice sheet can be attributed to surface melt, as we can see here. So the surface melt is largely constrained by the albedo of the ice sheet surface. The albedo changes based on the surface conditions. So for example, if there's snow, we have a high albedo, bare ice has a lower albedo, and then we get even lower albedos when we have light absorbing constituents such as dust, black carbon, or darkly pigmented surface algae. So the southwest ablation zone is the darkest region of the Greenland ice sheet and has also been shown to contribute significant surface melt, as you can see here. So the southwest dark zone is not only increasing in size and spatial extent, as we see here in bare ice extent and dark ice extent in orange, but it's also decreasing in albedo. So here we have the summertime albedo trend over the last couple of decades, and then a time series of that trend. So we see a declining albedo in that dark zone. So the southwest dark zone is primarily darkened by bare ice exposure and glacier algae colonization. Here we can see bare ice exposure, and then as that bare ice is exposed, it creates a habitat for glacier algae to colonize, and then we see really large glacier algae colonies come up in the summer. So significant melt has been attributed to both bare ice exposure and glacier algae growth. So here we see as we get higher season snowline elevation, so more bare ice exposure, we get increased total summer runoff. And that is due to kind of two compounding factors. The first is that bare ice lowers the albedo and causes more melt. And then also bare ice tends to be slicker. So any meltwater can just run off instead of getting trapped in a crustal surface and remelting. And so for bare ice, or for glacier algae in just 2017, it was estimated that between 4 and 6 gigatons of ice loss could be attributed just to glacier algae. So currently, CESM represents land bare ice albedo using parameterizations. So in the visible, we use a constant albedo of 0.6, and in the NIR, we use a constant albedo of 0.4, which we can see is not totally correct because the albedo of pure ice varies quite widely depending on the density or the volume of air present in it. We can see here in blue and purple. And the albedo influence of glacier algae is completely omitted, but we actually see a really large decline in albedo due to glacier algae. So our first step solution is SNCR AD version 4. This model is a single column heterogeneous multi-layer snow and ice model. It explicitly represents the optical properties of snow, ice, and a range of light absorbing constituents. So SNCR AD contains a combination of solutions that are already employed within CESM and E3SM. So within CESM, we have SNCR. It's in the community land model, snow radiated transfer scheme. It's used to calculate the albedo and fluxes of snow surfaces. And we have the Delta Eddington adding doubling solution, so the AD in our SNCR AD. This is currently used in the sea ice radiated transfer scheme to calculate the fluxes and albedo of sea ice, snow and ice columns. And within E3SM, we have SNCR AD, which is a predecessor to our model, which is currently called for snow radiated transfer scheme and the snow radiated transfer scheme in both the land and ice model. So SNCR AD kind of pulls all these things together. First, we calculate the optical properties of our ice grains, of air bubbles within an ice medium, and then of light absorbing constituents that are relevant for the area we're looking at. We put those things into SNCR v3 and run. That gives us the optical depth, the single scattering albedo, and the asymmetry parameter, which are the inherent optical properties that are then run through the Delta Eddington adding doubling solution. This solver can give us the spectral downwelling flux and albedos and absorption of each layer and the total column. So here's a quick schematic of what a column in the model looks like. So you can have as many snow and ice layers as you want, and the snow layers are represented as ice crystals within an air medium. The grain size generally tends to increase with depth. And then when you get to your first ice layer, we have a refractive boundary. This refractive boundary is meant to take into account the changing index of refraction between the air and ice medium. And then for our ice layers, we're now representing them as air bubbles within solid ice. And the bubbles tend to decrease in frequency and increase in size as you go down in the ice layer due to compaction. So now some preliminary results from our model. So SNCR ADV4 is able to simulate a wide range of realistic albedos. So as we see here, we can get very high albedos by snow, which is what we currently have in SNCR and CLM. And then we can also represent very dark low albedos and pure ice Fresnel reflection using the ice capabilities. This model can also very smoothly represent the transition between snow, firn, and ice albedo. As we see here, we can also represent very low specific surface areas and very low broadband albedos of pure dense ice. We also compared our model to a couple of sets of measurements from the Greenland ice sheet. The first set of measurements we compared to were taken by Joe Cook in 2017. He took measurements of clean powdered snow, clean aged snow, and coarse aged ice, and were able to reproduce all of these albedos quite well. And we also compared to measurements taken by Carl Bogild in 2010. Carl not only took measurements of clean snow, but also like quite dirty snow and ice. And because of our representation of light absorbing constituents, such as dust, black carbon, and glacier algae, we're able to simulate these albedos really well as well. So another set of comparisons and another promising result, we're able to compare to Antarctic albedo as well because of the flexible model scheme. And we're able to represent snow, fern, and ice albedos very similarly to measurements. So in conclusion, our model scheme is already compatible with CESM and E3SM. And if it's implemented in a fully coupled model, dynamic ice albedo simulations can improve our projections of surface melt and sea level rise in the future. And Snicker AD's flexible model scheme and explicit representation of optical properties allow it to be utilized anywhere snow and ice is present. Thank you. Do you guys have any questions?
Thanks, Chloe. You put us right back on time.
Tried my best.
Any questions for Chloe?
I have a question. This is Bill. This looks great. Are there plans to implement this in CESM or in the land model CTSM?
Yeah, our future steps or future goals are definitely to get it implemented in a fully coupled model.
Okay. Do you have a time frame for that?
No, hopefully sometime during my PhD, so the next 2 years.
Okay, sounds great.
Thanks.
Any more questions for Chloe? None? All right, well, if there's no more questions, then thank you very much for everybody who gave a talk this morning for these very good presentations. We are going to take a break for half an hour and reconvene at 10:30. For whoever would like to talk to individual person, we can arrange breakout rooms, just let us know. And otherwise, we will see each other again in half an hour. Thank you.
Thanks, Gunther.
Hi, Stephanie, are you here?
Yes, I'm here. Sorry, had to unmute.
Could you arrange a breakout room for Trevor, Hildebrand, and myself?
Yes, I have not done that, so I'll have to figure that out.
Oh, maybe I can then.
Oh, so I made you a co-host. If you click on more and click on breakout rooms, do you see that?
I cannot do, maybe here.
Well, maybe I can do it. Just let me click on this and then maybe I plug in the names. So it says assign manually. Create one breakout room. Let me see what happens when I do create. Assign. Okay, who do you want?
Trevor, Hildebrand.
Just the two of you.
Yes.
Okay.
Gunter, are you back?
I am.
Okay. I'm trying to send you a message, but it says you're not in this session. That's strange. Anyway.
I'm a ghost.
No, I think you're real. Well, let's give people maybe one more minute to get back, and then welcome, Courtney.
All right.
Courtney, would you like to go ahead and share your slides?
Sure, let me do that. All right. Oh, let's see.
So our next speaker is Courtney Schaefer, who works with Dan Martin at Lawrence Berkeley Laboratory. And she's going to talk about implications of using the shallow shelf approximations to model marine ice sheets. So welcome, please go ahead.
All right. Yes, thank you for the introduction. Thank you. I'll be talking about the understanding the implications of using the shallow shelf approximation for marine ice sheets. Okay, so the basis of this experiment, it's based on the MISMIP 3D intercomparison project. And so in this project, results showed a non-trivial difference between steady state grounding line positions between models using SSA and also higher order models like L1, L2, first order models, or the full Stokes model. So in the right-hand figure, you can see that so I've recreated the L1, L2 results and the SSA results using bicycles. And in the L1, L2 results, the grounding line position ended up around 530 kilometers. And for the SSA approximation, it ended up around 610 kilometers. And so there's this obvious difference here that we thought would be interesting to look more into. And so this quote from the A.C. Davis paper 2016, this is kind of the main background behind our experiment. And so I'll just repeat this. It says the initial grounding lines of the shallow shelf approximation models were around 80 kilometers downstream from the Stokes models, but the grounding line only moved about 20 kilometers in the perturbation experiment. That left an obvious question entirely unanswered. In a realistic simulation, with the model parameters chosen to match geometry and velocity derived from observations, and thus with prescribed initial conditions, does the SSA provide a good approximation to the Stokes model? And so that's what we hope to do in this experiment. We're basically treating MISMIP 3D as a realistic problem. And so the experiment that we'll be doing, I'll kind of outline that here. First, we will generate steady state L1, L2 results and treat those as the observations for the initialization. Two, we'll determine parameters by solving an inversion problem. And these parameters specifically are the basal friction coefficient and the viscosity coefficient. And these will be used to initialize the SSA model. And then third, we'll use these parameters that we solve for to try and reproduce the L1, L2 steady state position using this initialized SSA model. And then lastly, we'll introduce a perturbation to then observe the dynamic response of these models. So first I'll talk about how we generate these observations. Okay, so first of all, why are we using L1, L2 as observations? Well, in the MISMIP 3D experiment, the L1, L2 results behaved very similarly to the full Stokes model. And the full Stokes is kind of the gold standard for modeling. And so this provided a really good starting point for us because L1, L2 is less expensive. So in these figures, you can see the SCO6. This was the L1, L2 run using bicycles. And then in this right-hand figure, this is LFA1. This is the full Stokes model using the Elmer ice model. And so the black lines in both of these are the steady state grounding line positions that were generated. And you can see just how similar these positions were for both of these models. So we chose L1, L2 just because of how similar they were. Okay, so generating observations, we ran multiple runs with increasing resolution, and these were all based on the original problem specification of MISMIP 3D. And so we also used the Weertman sliding law in this one. And so in this left-hand figure, you can see that with increasing resolution, the values are converging towards some value. The results are converging towards some value. And so we want to observe, we want to look at that error a little more closely. And so taking the difference between these runs, we plotted that the rate of error, and at sub-kilometer resolutions, you can see that it is entering the an asymptotic regime, and it's tending towards a first order convergence. And so this is really nice to see because it basically tells us that our model is behaving as expected. And so we chose the 390.625 meter resolution for the remainder of the runs. And this is just because for higher resolution, the higher resolution runs that we did were a little more expensive for the later runs. And the 390.625 meter resolution seemed to be kind of like the sweet spot for us. So we chose that one to continue with. Okay, so now that we generated these observations, we'll then use these observations to solve the inversion problem. And so the approach that we use is the one in Cornford et al. Essentially, we have this objective function that is made up of both the mismatch and the Tikhonov penalty function. And so our goal essentially is to choose a basal friction coefficient and a viscosity multiplier that will minimize this objective function. And the way that that is performed is through a conjugate gradient method. Essentially, C and phi. C is the basal friction coefficient, and phi is the viscosity multiplier. Those are chosen through a conjugate gradient method such that this difference in velocity is minimized. This is the model velocity, and this is the observed velocity. So minimizing this will essentially minimize the objective function. Okay, so with these two variables that we have, we then have three different ways in which we can optimize these variables to find a u that minimizes the objective function, to find a velocity that minimizes this function. So in the first case, we have the case where basal friction and rheology are optimized, and we label that as true. We have the case where only basal friction coefficient is optimized and the rheology is kept constant. That's the true-false case. And then lastly, we have the situation where only rheology is optimized and basal friction is kept constant, and that is the false true case that we label. Okay, so after running the inversion experiments, so this is the case where where basal friction and viscosity are both optimized. And in this situation, we can see a very steep spike, and this happens at the grounding line. And so this spike appears essentially to prevent the grounding line from advancing. So this is a slippery spot that appears, and it prevents the ice from thickening at that point, and then also keeps the grounding line from advancing, because the SSA grounding line, like it wants to advance towards the SSA grounding line position. So we were trying to prevent that from happening. And so the steep spike kind of appears to prevent that. So also, again, this is based on the Weertman sliding law. So for any other sliding laws, you would probably still be able to see the spike, but it just wouldn't be as pronounced. So again, because this is both basal friction and viscosity being optimized, we can also see the viscosity changing here. And so there is a very infinitesimal change in phi for the viscosity coefficient, but we could see that the basal friction coefficient solve primarily dominates this just from how infinitesimal this change is. Okay, so in the situation where only the basal friction coefficient is optimized, again, we see this spike. And And then again, the viscosity coefficient is kept constant at a value of 1. And so we see this very similar spike. And again, this is just to keep the grounding line position from advancing. And this looks very similar to the first one, again, because of how bicycles solves bicycles solves inversion. The basal friction coefficient dominates in the inversion problem, and the viscosity coefficient solve happens after the basal friction coefficient solve. So in the situation where only the viscosity coefficient is optimized is where we see a little more interesting behavior. So again, basal friction is kept constant, but then we can see this change in the viscosity coefficient. So right before the grounding line, there's about a 20% change in the viscosity coefficient, and then it increases pretty steadily afterwards and then mellows out. So this is interesting because the SSA model can't represent vertical shearing. And so this viscosity coefficient kind of comes into play to counteract that missing physics. And so this is the kind of like the missing element that phi makes up for with SSA. Okay, so now that we were able to come up with those parameters, both C and phi, we want to be able to reproduce the L1, L2 steady state. So again, we want to be able to reproduce this L1, L2 stable steady state, but we found actually that the only case that was able to reproduce that steady state was that last scenario where only the viscosity coefficient is optimized. And so you can see that with this flat light blue line here. In the other situations, it ventured off and it found a new stable steady state. And this new stable steady state was actually the original SSA grounding line position. And so why did this happen? We were pretty sure it's because of the fact of how narrow those slippery spots were. So because of how narrow those slippery spots were, the grounding line was then unstable to any sort of small perturbation. So once the grounding line falls off that slippery spot, it can then find a new steady state. And so that's what's happened here. Okay, so lastly, we're going to introduce a perturbation to see how to see the dynamic response of these models. So what we did was we decreased the accumulation by 20%, and then we decreased accumulation by 20% for all 3 of the cases, including the original L1, L2 model. So there's two things to point out here. So first of all, the cases where basal friction coefficient was optimized was again unsuccessful. And this is unsurprising because of the fact that they initially were unable to maintain that steady state. So again, it ventures off and it finds a new stable steady state, but the grounding line still advances here, even though you would probably expect with decreased accumulation that the grounding line should retreat. But we see that it advances here. The other thing that I want to point out is the response of the case where only rheology was optimized. So and that's this dark blue line here. We see that it does indeed retreat compared to this light blue line, but this retreat does not match this red line, which is the response of the original L1, L2 model with the 20% decrease. And so we would expect that these lines would match up, but they don't. And so we're underpredicting the behavior of the SSA model with the 20% decrease. And so we think this is because of the fact that the viscosity coefficient that we solve for is time independent. And so it can't evolve with time, and so we're under predicting that response. So in summary, again, with how narrow those basal friction values were for both cases where the basal friction coefficient was optimized, we found that it was hard to force the grounding line, the SSA grounding line, to match the original L1, L2 stable steady state without falling off that slippery spot. However, we were able to match with rheology, and so this was nice to see. But even though we were able to match with rheology, we were then unsuccessful in predicting the dynamic response due to the fact that phi was time independent. So overall, by treating MISMIT 3D like a real-world problem, we were unable to get SSA to behave as we expected. So this might be different if we were to include a different sliding law or if buttressing was present. And so for future work, we are going to be continuing this experiment with MISMIT Plus, and MISMIT Plus includes ice shelf buttressing. And so with this, we're hoping this is going to be more effective in reproducing the stable steady state grounding line positions for all three optimization methods that we had. And then for a real world problem like the Amundsen Sea embayment, and this has Thwaites and Pine Island. And so these are similar to MISMIT 3D and the MISMIT Plus problem, so we're hoping to see some correlation there. And yeah, that's it. Thank you.
Thank you, Courtney. Time for one question.
Sorry, Bill, I don't have a raised hand option. This is Olga, but I have a quick question.
Go ahead, please.
What were the bad slopes and what was the geometry you were trying to play with? Was it what was with the trough, or what's the magnitude of bad slopes were you considering?
The slopes. Sorry, you were cutting out just a little bit for me. Can you repeat that question?
Bad slopes. What was the geometry bad that you considered? Sorry.
Oh, the bed slope. Okay, that's a good question. Okay, so it was a linear bed slope. And
no, the bed slope was constant then. So if the bed was linear, then the slope was constant. What's the magnitude?
That's a good question. I don't remember exactly, but this is based on the original MISMIT 3D.
What was so your results might be subject to that value because yeah, effectively the grounding line position depends on the bed slope, and so small changes in the bed slope would be large changes in the thickness. So in that regard, it's all subject to the bed slope, not only the magnitude, but also if you were to change the bed configuration instead of the linear bed, do something different. Again, the results might be quite different.
Yeah, of course. And so, I mean, this is all just based on if we were treating MISMIT 3D like a real world problem. So yeah, of course, there might be a lot of differences if we were to change different parameters.
Thanks.
Okay, thank you again. We'll now move on to a series of model update talks, starting with the Land Ice Working Group Software Liaison, Kate Thayer-Calder. Kate's going to give us an update on recent and future work related to software engineering and model diagnostics. Whenever you're ready, Kate.
Okay, I shared my screen before unmuting, and that's something I've never done before. Can you see my presentation?
Yep, see it just fine, thanks.
Great. Let's move this so that I can see it myself and present. All right, so hi everybody, my name is Kate Thayer-Calder. I am the software engineering liaison for the Land Ice Working Group here at NCAR and in CGD. I put my email here, so if you guys are having questions or issues with running land ice related simulations in CESM, I am the person to contact about that. I'm going to give you a quick talk on the work that we've done in the last year on software and diagnostics with the Land Ice Working Group at NCAR. I know that these sort of software engineering talks can be very text heavy. I don't have a lot of cool visualizations or plots to show. So I usually try to find something kind of fun to add to each slide. And this year you get Bernie Sanders sitting in a folding chair. So yes, this meme is 2 weeks old and people are sick of seeing it, but you'll have to bear with me for about 10 more minutes. One of the first things that I wanted to talk about is the current, actually I'm going to move this so that I can actually see my slides a little bit better. The current development of CESM. There's a lot of different releases over the last year and a lot of different sort of development pathways for the model. So I'm going to go over these pretty quickly, but and make sure that you guys understand what we've done and where we're headed. The CMIP replicating series of releases are the CESM 2.1 series of model releases. So since the last winter meeting, CESM 2.13.3 was released. So that was late February last year. And all that included was some Python fixes to manage externals. Since then, we've been working on the CESM 2.1.4 release, which I think is likely to be released this spring. We've had several release candidates and we're getting very close to what will be in that model. And that does include support for COM sets for the SSP extensions from 2100 to 2300, that's SSP 585 and SSP 534 overshoot experiments. The WACM COM sets have already been done. We have started simulations with active ice sheets, which I'll talk about in a later slide. But the CAM-based simulations have not been completed, and those COM sets may or may not end up in this release. This release also includes support for the large ensemble, which is a CSM2 project being run in Korea right now. They have over 100 ensemble members, and I just checked in with Jim Edwards yesterday. He says it's about 75% complete right now. So they've been working on this for a long time, and it's a huge project. But the COM sets and the software support for that are going to be released in CSM 2.1.4. And I can't move to my next slide now, probably because I'm not, there it is. Okay, there was a new science release last August, CSM 2.2. So this will not replicate the CMIP series of experiments, but it does include CAM 6.3, which is a new version of CAM, and it supports the SC and FEV3 dicores. There's some changes and improvements to CLM, and a functional version of MOM6 was released with this version of the model. CSM 2.2 will have a 2.2.1 bug fixes. So if you work with the 2.2 model that was released in August, you should keep an eye out for the next release to have bug fixes that are not climate changing associated with that. And then we are working on the CSM 2.3, the next science changing release. So this is still very early. It looks like it's going to include things like PiO2 as a default, which has required a huge amount of work for the CAM software engineers. And then the new OPSI coupler replacing the MCT coupler, which helps us in the Land Ice Working Group support multiple ice sheets. So that will be a big one for our work too, going forward. And it's likely we will include some of our updates to the land ice in this release as well. So what have we done over the last year? 2020, I went back and looked at my meeting slides from last year, and things did not quite turn out the way that I expected they would in early February 2020. So we did get quite a bit started, but didn't get as much done as we were hoping for. We did finish the ISMIP self cases, which are a series of standalone T cases that replicate the coupled simulations that we did for ISMIP. So those are available on the CMIP data archive now, if anybody's interested in the results of those. We started working on runtime topography updating strategies. So one of the things that we learned over the course of finishing our ISMIP simulations is that the coupling between the ice sheet height and the atmosphere being done offline is a huge source of failure. It's a failure point. So we've been working on trying to improve that situation and have come up with a couple different possibilities, but nothing has been particularly finalized for that. However, I am going to talk about the current strategy that is supported by me or our group in the documentation in a slide from now. We joined the GHub project, which is a diagnostics conglomeration website and land ice group project out of the University of Albany in New York. And this will provide some funding to scientists in the NNCAR part of the land ice working group to hopefully focus on diagnostics this year, which is something that has been in my slides for 2 years now. So hopefully we'll get better work done on that this year. The SSP 585 extension from the year 2100 to the year 2300 was a big project this year, and it is now actually running, albeit a little bit slowly because we probably need to update our PE layout to get a more efficient usage of the machine. And it's on year 2111 right now. So it's going. And the SSP 534 extension has a case set up, and I'm gathering the forcing files for that right now. And our hope is to have that started and running in parallel with the 585 in a week or two. This year we did make some documentation updates, as I mentioned previously, and I'll go over those in just a second. We are working currently to bring in a new, more efficient version of CESM to the master of CESM, the master branch in GitHub, and then that will be supported in CESM releases going forward. And I believe that Gunter is going to talk more about that in his update just coming up in a minute. And then we're working right now on adding support for the fully coupled Antarctica ice sheet simulations, which Bill Sachs gave a really nice presentation on yesterday. And I'm not going to go into detail too much on that other than to mention that it is a big project taking up developer time right now. So what are the plans for 2021? Well, we've got to finish these XSP extension runs, and hopefully that should be done in the next 6 to 8 weeks. We have this new CESM code coming in, and that needs to be validated and tested, but we're in a good place for that. Currently, it's been used by several people, and scientifically, it's looking pretty good. We are really hoping to focus on getting work done on a land ice working group diagnostics package, especially with aid from this GHub project, and continuing work on finding a better system for doing topography updating at runtime during the model. We'll be finalizing the Antarctica and the Antarctica support and working on Neopsy support for the future of CESM, and looking into some CESM releases this year with updated documentation for the model, including build support on laptops. And I see Heiko's hand is up. I'm willing to answer a question right now. Do you want to unmute yourself?
Hey, Kate, thanks a lot. This is really great. I have one specific question about the diagnostics.
Sure.
Which direction is this going? Is this going to be based on some kind of NCL stuff or more like Python oriented? Or what is your perspective there?
Yeah, I'm gonna, so we're gonna have a whole half hour for discussion. And I know a lot of us would love to talk about diagnostics more specifically then, so we can get into the details there, but definitely aiming for more modern technologies like Python, because NCL is gonna be losing support from NCAR over the next few years. All of the NCL people have retired, as far as I know. It's just not a commonly used technology as much as it used to be. So,
okay,
yeah.
Great, thanks.
No problem. All right, so go back over here.
Kate, we have a question for, sorry, go ahead and finish, and then we'll move to a couple of questions in the chat.
Okay, that sounds good. So I mentioned previously, we did a few documentation updates this year, and I always like to put a link to the CESM and CESM documentation out there, because this is a great source for answering questions a lot of people have had in the past. One of the big parts of the documentation update that we've put in is this year, you can see under number 3, running fully coupled ice sheets under BCOM sets, is the topography updating workflow. So if you're using a version of CESM 2.1.1 or greater, and that includes 2.2 or 2.2.1 or anything where the second number is larger than 1, then you can use these instructions to set up a CESM-based workflow that will automatically run the topography updater for you every 10 years of your simulation. So that's a useful workflow that has worked well for some very large simulations that have already been done. And the documentation for how to set it up is all here online. There's also more documentation added to cover accelerating the ice sheet relative to CESM. So another common question or workflow that wasn't well covered before is how to run the ice sheet faster relative to CESM. And now that is in the documentation as well. And then finally, we are going to have, as I mentioned previously, a discussion in half an hour. And one of the things that we'd love to have input on is what we should have as a land ice working group diagnostics package. And again, this has been something we've been talking about for as long as I've been a software liaison. 2 years ago, we had a lot of interest and enthusiasm about this, and we had separate meetings and a lot of input. And there's definitely a broad outline for what people want, but we haven't gotten into the details for that because we haven't been able to start actual development of it. Because I just have not had the time in the last 2 years. So we do have a mandate and funding now. The GHub project, this is their website, ghub.org, and this is kind of what it looks like minus Bernie Sanders. I thought he looked cool there, but he's not on the actual website. And the goal of this project is to bring together data sets, models, observations from a lot of different places, all related to ice sheets and ice sheet science, and help form some synergy. So we can develop diagnostics that could be useful for a lot of other models, and that could be specific for our model, and then publish those diagnostics through the GHub portal. Our plan is to try to develop something that is extremely useful for large coupled simulations for CESM and would work with the post-processing tools that we have in CESM right now, but it could also be useful for other modelers and would include observations and data sets from other parts of ice sheet science that would be useful in that case. So we have some notes from past discussions. Bill and I were discussing last week, and we think some notes might be left in the Mesa lab that we haven't been able to access in a year. So there may be some of the discussion that is going to feel redundant to some people, or like we're starting over again. But again, we should talk about what people want or are interested in during the discussion time period at 11:30. And if you have any other thoughts or things that you don't want to stick around and talk about on the Zoom here, you can feel free to contact me. Here's my email address again. And I'd be happy to hear what information or what thoughts and opinions people have on what would be very useful for ice sheet model diagnostics as we build this package. So that's all I've got. And we can take some questions now. Thank you.
Thank you, Kate. I'll start off with a question that Chuck posed in the chat.
Mm-hmm.
He says, do you anticipate any significant reprogramming required for CESM when the new HP Cray supercomputer is installed sometime within the next year or so?
No, we don't anticipate a large amount of reprogramming required. Likely the support for porting our system to that will be handled mostly by SEAM. The way that CESM is architectured, it's easy, relatively easy to port between different supercomputers. And CISL has done a good job in the past of not requiring huge amounts of changes for our code. They actually do run our code on systems, parts of the CSM model, to make sure that the systems they are testing out before they purchase will work as a mitigation, like will work in being able to be migrated as we go. Does that make sense?
Quick follow-up. Do you anticipate that there will be, let's say, encouragement for model developers to write more GPU-friendly code?
Yeah, so we are hoping one of the improvements in the speed and capabilities of this model is that something like 20 to 30% of the processing power will be handled by GPUs. And in the past, CESM has had trouble with GPUs because the porting has been difficult, but there's been several groups in CISL who have taken parts of CESM and already done some work on it to prep it for use in those GPUs. So I also work with atmospheric microphysics, and we recently went through a process where that part of the atmospheric model is now prepped and ready to be used with GPU code. So I imagine that a fair amount of the model will be what's called offloaded, where those particular parameterizations or intensive pieces that can be pulled out and model and sent to GPUs will be. I'm not sure how that will be used for CISM going forward. We haven't discussed that plan yet, but this next computer won't be fully available to the community until about a year from now. So there's still time to discuss and plan that.
There may be parts of CISM that would be GPU friendly, so that's something we can discuss in the coming months.
Absolutely. Hi, right. Betty. Should we go with Betty or should we do another one from the comments?
Let's do one more question. One question from Betty, then we'll move on to the next talk.
Okay.
Okay, just a quick comment and question. Since it takes a while to get diagnostics ready, and you mentioned now you have the resources, but maybe the Land Ice Working Group, particularly for CISM, could consider having user-contributed diagnostics. I saw some really nice diagnostics plots in the talks this morning. Mm-hmm. So, you know, as something that may not go in the package, but still would be very useful for the users.
Absolutely. Yeah, again, we can talk about this later, but I'm not the person who is going to develop the actual plots that are used in this. Hopefully that comes from the community. And any nice scientific and interesting diagnostics that people feel would be very useful, we should be able to easily integrate those. And I would like this to be almost a living package where we can remove things that are less useful over time and add in new ones as they come. I don't want this to be like the AMWG specifically, which seems to be, you know, the same 300 plots every single time. So that's one of my goals.
Okay, thanks again, Kate. And we will come back to this topic during the discussion. Next talk will be a model update talk from Gunter. And I believe we're going to tag team, so I'm going to step in at some point, but Gunter's going to start out.
Okay. Good morning, everybody. It's going to be a very quick talk where I'm going to mention some model development that the latest version of CESM is going to look like. And this model development were possible by, a lot of people: Bill Lipscomb, myself, Kate Calder, Bill Sachs, Mariana Verdenstein, Eric Kluzik, Gustavo Marquez, Alper Tuntas, Alia Summers, and many others. So if you were there yesterday during the first day of the Land Ice Working Group, there was a lot of talk actually that showed results from a development branch that was used for mini simulations. And those ones include model development that are now that will be pushed in the CESM 2.2 release that we hope to release by the end of FY 2021. And as Kate mentioned, sometimes time flies by, and when you look at the older slides, well, I think we had hope for this for such a release 6 months ago. Well, we have COVID to blame for this. But what you're going to get in this new release pretty much is highlighted in this table, and a lot of it is already underway and done. Among those, the Greenland parameterizations for basal stress and basal melting, new physics option for sub-ice shelf melting, for Antarctica, inversion for basal sliding and subshelf melting parameters for spin-ups and other experiments. Performance improvement, an accelerated Picard solver, which makes conversion of the solver faster, with and ignoring ice free ocean cells that Bill put in place, which is a very nice feature in that you can run CESM for one time step. It can be very short, and then CESM takes care of analyzing where ocean cells are located, and then it would give you a new grid where it will spare the processes to actually compute any dynamics on those ocean cells. So it led to a speed up of 20 to 30%. We have worked on support for standalone Antarctic simulation, including MIP6 projections. So all of these features are done. And what's in progress right now is support for partly coupled Antarctic simulation in CESM that we hope to scientifically validate and move over to the done column. There are two articles that are about that we have written for standalone ice sheet simulations. One that CESM in MIP6 papers that is almost ready to be published. It's almost in the press. And the one about the standalone grounding line parameterization that I presented about yesterday that is under review in the cryosphere discussion. What needs to be started is to update the model documentation and to create new test cases, new examples in the standalone repository, and that I will take care of shortly. Those standalone test cases will be about Greenland and Antarctica.
Okay, I think I'm going to jump in here. Looking ahead beyond CESM 2.2, we'd like to do a CESM 3 release at some time in the future. And I'm not going to predict a date today because I'm notoriously bad at estimating how long it will take to do things. But I will say that for ISMIP6, we found it very hard to spin up Antarctica to a present day state that's consistent with observations in terms of where the grounding lines are and how fast the ice is moving and where the calving front is. And so we'd like to, over the next couple of years or so, to put a lot of effort into improving our physics parameterization so that we can, so that they're more physical and less prescribed. So in particular, Aaliyah Summers, who has been a postdoc and is beginning a new postdoc, has developed a basal hydrology model called Shakti, which we would like to implement in CESM, and if possible, get that calibrated and working for both ice sheets. We would like to explore some calving schemes for Antarctica such that we can do a better job at reproducing the location of the calving front without simply prescribing the calving front with a mask. We've already implemented some subshelf melting parameterizations where we have a function or a choice of functions that convert ocean thermal forcing to a sub-ice shelf melt rate just by extrapolating thermal forcing beneath ice shelves. We'd like to do something that has more physics in it, maybe Coriolis effects of topography. And one candidate for that is a reduced physics model that's been proposed by Adrian Jenkins. The isostasy in CESM is more or less the same as it was in when it was the Glimmer model some years ago. We did a sort of quick and dirty parallelization of the isostasy, but that parallelization does not scale well. So we want to look at both scalable isostasy and also a more physically realistic isostasy. And one of the goals we have as we undertake these physics improvements is to be able to spin up Antarctica to a reasonable modern state, as we showed we could do for Greenland with the CESM 2.1 description paper that came out a couple of years ago. We would like to have a reasonable Antarctic state using new physics schemes and prescribing as little as possible at a resolution of perhaps 2 kilometers or maybe even 1 kilometer without having to rely as much on inversion. For example, inverting for basal friction parameters in every grounded grid cell. We'd like to do a lot less data fitting and a lot more physics that we have confidence on for simulations that go beyond a century, maybe several centuries into the future, or even simulations lasting multiple millennia when we're exploring paleoclimates. So this is a long-term goal, and if anyone has ideas for any of these sorts of schemes that you'd like to contribute to, please let us know. We absolutely welcome more CESM developers. Back to you, Gunter. I think you're still muted, Gunter.
Thanks, sorry about that. In the discussion time that we're going to have at the end of the session, we'd like, along the diagnostic discussion that Kate mentioned too, we would also like to invite any feedback on what other features that need to be prioritized in the CESM development. So if you have any thoughts, please share them with us. And this is pretty much it. Some more information. So the CSM tutorial this year is going to take place from August 9th to 13th. The application is open and will close on March 1st at 11:59 p.m. So at midnight would be too late. And it will be fully remote again this year, just as it was last year. And again, some more contact information. If you need to contact the Land Ice Working Group, you can contact the co-chairs, Bill Lipscomb, Ian Leonards, or Kate and I for any scientific liaison question or software liaison questions. And yeah, that's all. Thank you very much.
Okay. Thank you, Gunter. And again, I would encourage early career scientists especially to sign up for the CESM tutorial, apply for the CESM tutorial if you haven't taken that before. Our next update will be from Adam Harrington, who has done a lot of work in developing and exploring variable resolution simulations with CESM, including the high mountain Asia simulations that Renee spoke about earlier. Adam's now going to give us an update on variable resolution CESM with Arctic configurations. So please, thanks, Adam.
Yeah, you can hear me, right?
Yep.
All right. I'm going to give you an update here. I am now a project scientist, and my primary mandate is no longer variable resolution, but I still make time for it. This is just a cool visualization I put together with Matt Ream and Sizzle, just showing the model topography draped with streamlines draped over it in our 8th degree run. So we also put together a movie, and it's very preliminary, but I'm going to show you what we've got so far from this 8th degree Arctic simulation. I'm going to show a couple new science results from the FHIST runs using the Arctic and the Arctic GRIS grid, which, by the way, run out of the box with these grid aliases for CSM 2.2. And then I'll finish off with a BComp set. So we're trying to get this Arctic run with a couple of the oceans so we can run it over the historical period into the future, which requires some tuning. So the visualization, I'm going to stop the show, go to the visualization, press play. Okay, hopefully everyone can see that. So what you're looking at is the 8th degree run, and this is the total precipitable water with some depth added to it. And the idea is that this may look like your typical GCM at 1 degree, but it actually is not. So we fade to the grid that shows that we have regional refinement over the Arctic, 1/4 degree, the 8th degree over Greenland. And note these are just the element boundaries, so they're not the grid spacing. Now we're going to fade into some streamlines with the precipitation overlaying on them. And you can see these really cool orographic precipitation events on southeast Greenland. We're experimenting with different contours that bring out the colors better. We had a really good one this morning, but the timestamps weren't lined up. We might actually use the model topography instead of this DEM in order to really show the transition to the higher resolution region better. So this is the actual model topography here with the streamlines draped over it. I think it looks pretty cool. A little too much red for my liking, a little too fast for my liking, but it's going to be something like this. So back to the presentation, if it ever loads. And so again, there's these 16 nodal points in each spectral element that really delineate the grid spacing. And so we're going to overlay that as well. So next, I'm just going to talk quickly about a quick science update. So for the Arctic run, the quarter-degree run, I ran the Tempest Extremes tracker on there, which is really nice because it you can run the tracker on unstructured grids. But all it provides you is with a storm center and a trajectory. And so I made a storm compositor that works on the unstructured grid where it looks at the storm center and then it scans in a 20-degree window about it, and you can save these fields. And so this is what the composite mean of all the storms and all the tracks for all storms poleward of 45 degree north, which is where the refinement occurs. And so this is what the storm composite looks like. And you see that nice comma shape. And so you can also perform statistics in this domain on all the members that were used to make this composite. And so I have PDF of PREC-Ts by month. I'm comparing the red is the Arctic, and then the blue is the NE30 PG3, so the 1 degree control. And then the light blue is the same, but with a smaller physics time step that matches the Arctic grid. And so when you compare light blue to red, it's purely the effect of the increase in spatial resolution. And then ERA5, I ran the tracker on that for comparison. And so you can see, like in the summer especially, there tends to be more extreme precipitation events than are realized in the 1 degree model. And so our Arctic grid is approaching that of the ERA5 solution, which we generally view favorably, but it's certainly a matter of debate on whether we're just comparing. ERA5 is run with a 1/4 degree atmosphere model, which is what our Arctic refinement is. And so whether the data assimilation is actually constraining these extremes or whether this is pure model behavior is up for debate. But nonetheless, it's always good to have your model match ERA5, generally speaking. So this isn't necessarily about variable resolution, but this is very relevant to where our atmosphere dicores or our workhorse dicores are going to be going in CSM2. We're going to be moving away from the latitude longitude grids to quasi-uniform grids. And so what I'm showing here is just this poleward projection of the NE30 PG3. And this is not the element grid. This is different than the variable resolution dynamical core, and it's denoted by this PG3 modifier. And what that means is we take the element and we chop it up into 3x3 control volumes, and the physical parameterizations are therefore solved on the infinite volume grid, and as is the tracer advection, while the dry dynamics are solved on the spectral element grid with those nodal point values. And so this is NE30 PG2, which is the physical parameterizations are actually solved on a coarser grid where you chop up the element into 2x2 control volumes. And so the dicore resolution is the same, it's just the physics resolution is different. And this is your finite volume 2 degree and your finite volume 1 degree. And I've computed the average grid spacing averaged over the Greenland ice mask. And this is, one of the main benefit of using these latitude longitude grids is you get the higher resolution at the poles. And so this light blue is the finite volume 1 degree. And you can see it's about a 60-kilometer grid spacing over Greenland compared to NE30 PG3, which is quasi-uniform everywhere at 111. And so that you do have these benefits. And so when we're moving away from here to here, it's worth asking the question is, are we losing are we not resolving as many processes over Greenland because of that? To some extent, the answer is it doesn't make too big of a difference because we have these polar filters that go like the sine of the latitude square that basically attack features that are trying to grow at the grid scale, these small grid cells, from ever really gaining any muster. But that's only true in the atmosphere model. The land model doesn't have any such constraints. So I just wanted to look at the surface mass balance integrated over the Greenland ice sheet area for all these different grids. And here I'm showing the area of the Greenland ice sheet, and it's represented as an error from the data set that you use to create the Greenland ice sheet ice mask.
Hey,
So,
Adam, 2 minutes.
Okay. So basically, what I'm saying is that the data set you use to create the Greenland ice sheet mask in the model, when you go to coarser resolutions, you have a small error that tends to make it a little bit larger, so about 1%. But if you compare this to RACMO, so RACMO is going to be the observations, quote unquote, that I'll be comparing to. RACMO is a much smaller ice sheet, about 3% smaller than what we use. And so I decided when I was going to compare these integrals over the ice mask to just map everything on all these grids to a common grid. And so I chose the finite volume 2-degree model. And so the precip rate over time integrated over the ice sheet in gigatons per year, the pink and the purple, which are the variable resolutions, obviously do a very good job comparing favorably to RACMO. Finite volume does pretty good, and it does better than the quasi-uniform 1-degree versions. And so there does seem to be some improvement in using the latitude-longitude grid over the quasi-uniform, and that's especially true in the runoff field, which is primarily a CLM calculation that doesn't have any polar filter that would reduce the impact of the higher resolution over Greenland. And so the finite volume solution actually looked really pretty good for the runoff, and not so great for the 1-degree. So I probably don't have very much time, but I just want to quickly mention we need to tune when we're coupling this to the ocean, we really need to tune it because I ran out the B1850 with the Arctic grid for way too long and wasted way too many core hours to realize that I'm in a climate that's really way too far away from the pre-industrial, which is given by the CMIP6 control here. And so I need to tune it. And so what I'm doing is a lot of the sensitivities, because I'm using a smaller physics time step. So I'm just going to tune the 1-degree model with a small physics time step. And long story short, I was able to bring it into balance. That's given by the red line. This is the restom. And the problem is, one issue that is worth discussing is that the way I do it might not be the best way. I'm basically increasing the cloudiness. So this is the shortwave cloud forcing difference from the observations. And it's basically saying I'm putting a bunch of cloud over here and here to cool the climate to bring it into balance. And compared to any 30 out of the box with the regular physics time step, it's a little too cloudy. So I don't know if I'm going to stick with this or try some other tuning parameters. I'll stop there. I know I'm over time.
Yeah. Thank you, Adam. Any questions for Adam? Okay, if not, we'll move on to the next speaker. We can always circle back during the discussion. Our last speaker is Jed Brown. For those who may not know Jed, he was a lead author of the parallel ice sheet model at the time it was first released. Jed is now a computer scientist at CU Boulder.
That jacket would be hard to clean. It's like a faucet. Well, it's got a down in it, I think.
Hi.
Anyway, go ahead and start.
So I basically want to have a kind of open-ended conversation about how we package data for glaciology is kind of more broader geophysics, but so the basic concern is the way that we tend to do things now, I think is not a good use of skills, and it makes it so that when people want to do model-based inference, they have to do kind of heroic amounts of both data engineering and model development and analysis. And so the kind of basic goal here, and I guess I kind of sketch things up in the setting of Bayesian inference, though the ingredients are much the same otherwise. But this diagram's sort of cribbed from more of a engineering terminology. But basically, the idea is there are inputs which you may know certainly or very uncertainly. Nature behaves given those inputs in some way, and there are observable states, which can be things like surface velocities. and everything else that we like observe about an ice sheet, for example. That ultimately produces some collection of data. And when we set up our models, we do some pre-processing. We approximate kind of our understanding of the current state. There may be kind of parameters living over there because we don't know the state completely. That's part of the, often we call that data assimilation. There's then our PDE solvers, which have parameters because usually we don't understand materials exactly. We don't understand like enough about these processes. There are various things that are parameterized. So there's a set of parameters and there's simulated state, which from a modeler's standpoint, we tend to think about this as like entire fields. And then perhaps we boil it down into aggregated quantities or whatever. Perhaps we measure surface velocities instead of velocity everywhere at depth. And these are simulated or synthetic observations. And if we're trying to do inference with this sort of model, we have some sort of loss function or log posterior that depends on the simulated observations, the data, the actual observations, and this set of parameters. And so typically there's some kind of prior over the parameters. When the parameters are high dimensional, like bathymetry, then this prior is quite interesting. It has a lot of rich structure that depends on other data as well. It's maybe not the thing that we're simulating, but there are other imperfect observations. They're sparse, they have errors. There's then what our model predicts. So we take parameters in and the model predicts something. There's an observation operator, which may in general be nonlinear. And we want to compare that with data. And what I've written out here is kind of it's a linear model of the uncertainty. So there's some observational, this is an inverse covariance norm, but there's a norm that relates to the observation operator, and you can think about that as being kind of the first, this is supposed to be a fraction, probability of data given parameters. This is known as a likelihood, and the ratio here is known as an evidence. And so the basic idea, kind of my suggestion here and the starting point, I think, for a conversation is that what I would like to have is where modelers produce synthetic observations. That's their job. They can work on whatever grids they want. They produce synthetic observations that are interpretable to a system that can look at data. And then we look at the evidence given by that data. And this is where all of the correlation models can live. This also gets us away from some, at least conceptually, from some of the big problems that we encounter. For example, when we look at the bed maps, those are derived largely from flight track data. The flight track data is not extremely dense, and so there are significant kriging artifacts. And if you naively run an ice stream down, the ice down an outlet glacier, some deep channel, the kriging artifacts they're sort of like if you had, say, Yosemite Valley and you had huge landslides that came down and just completely blocked off the valley in places. And of course, if you ran water down that, you would have huge lakes show up. Similarly, we have these kriging artifacts. We run ice down it and we get non-physical flow velocities there. And it really undermines our ability to understand the dynamic response. And so I would love for a way for us to get away from this kind of heavy reliance on these kriging artifacts and then not having a reasonable model. We don't have like, some appropriate covariance for those kriging artifacts. It's a very messy kind of probability structure. And so the idea would be instead we can have a first-class product from the data. Instead of it being gridded data, it becomes a function, and we can package this in libraries. It's a function that evaluates something like the log of the evidence. So this includes any sort of observational covariance model, even non-Gaussian models. The thing that it takes in are these synthetic observations. And it basically says, how compatible is that with the data? For efficient higher level algorithms, we have to be able to evaluate gradients, but that's a thing that can be entirely contained within this sort of a package. And this also gives reasonable ingredients so that people who are maybe different groups that develop models that are doing this level of data engineering, that are creating these sort of products, other people can come in and run sensitivity studies, like risk measures, optimization of parameters, which is often kind of evaluating modes of a posterior distribution, if you think Bayesian. And these are the right interfaces to connect with machine learning tools and probabilistic programming tools. And so this would allow us to exploit libraries more effectively. Basically, I wanted to have a conversation about our ability as a community to kind of break this apart and have the concepts here on this kind of middle point be more visible and have more buy-in from people who are currently doing data preparation and maybe not modelers. So sorry about the tons of background noise. I'll mute now.
Thank you, Jed. Any questions for Jed? I'll start with one. You mentioned the Kriging artifacts in something like BedMap or BedMachine basal topography data. Could you fill in a little bit with examples what this methodology would look like as compared to what people typically do now, which is we take typically now we would download a BedMachine data set, we would interpolate it to our ice sheet grid and take it as truth. So what are you suggesting would be better and different?
So we could do model-based inference, which would give us a bed that's actually compatible with the flow observations. So right now, people tend to use Kriging, and then there have been some like corrections to that based on kind of local integrals to help remove some of the artifacts, but it's not compatible in any sense with the flow model. What this would involve is actually, yes, both kids having outbursts, lovely. This may involve like good initial guesses that might be gridded data, that it hopefully would actually be better gridded data than BedMap. But we would be able to, for a particular flow model and a few optimization iterations, we would be able to tune a BedMap for for that purpose.
So would this be similar to the Morlingham mass conserving bed method, only it would be tailored for each individual flow model?
Yeah, because honestly, we don't know the difference, but we want a flow model that's compatible with the surface observations. We know surface velocities a lot better than we know the bed where there's no flight track data. And so it's actually perfectly reasonable that we run forward predictions using different bed maps for different flow models, because those are the bed maps that are most compatible with the surface observations. And thus we expect to respond to changes in say, climate forcing, we expect them to respond in a more compatible way. Of course, with this kind of technique, you can also sample over an ensemble of compatible bed models, but those bed models should be better because they're compatible with the surface. And this is something that people have they have tried, but not particularly successfully, I think largely due to it's difficult to build a team that that like puts together all of these components. But I think there's a lot of potential. And I think it's the right kind of breakdown of whose job it is to create which pieces, because it's where the expertise actually lies versus, say, modelers trying to reverse engineer a kriging process.
Any other questions for Jen? Okay, if not, let's go to general discussion. Chuck's had a question in the chat for some time, which I'll start off with. He says, CISL offers large computer resource allocations to a limited number of projects as friendly users during the startup months for new supercomputers. Does the Landice Group have a suggested project or projects that will be shovel ready to make use of a large allocation early in 2022? So I guess I would put it out to people on the call. Do you have ideas for large shovel-ready projects? Should that allocation become available in about a year? This would be in addition to what we already have in our 2-year CISL allocation. Okay, so this is an offer to get first in line for free computer time if you would like. Any thoughts? Would we want to do variable resolution runs? More of the kind of runs that Miren showed with coupled Greenland?
So there's a comment by Samar as HMA work already has allocated resources, correct? And the answer is yes. And if we have way more allocation, I suppose that we could run more experiments along those ways, this way. If you have something new to suggest that's missing for your project.
I would, so yeah, we have already quite a lot of computing time allocated to us, especially for the year 2 of the current CSL proposal for variable resolution experiments. One thing I'll just throw out there that we feel like we don't have enough computing resources to do with variable resolution is to run ensembles. And so maybe once I illustrate, God willing, that the Arctic grid, for example, runs with a coupled ocean and produces a reasonable climate and climate sensitivity, then I would absolutely think we would, that running ensembles to constrain that uncertainty would have provide a strong scientific foundation for the variable resolution results.
I think that's a great suggestion. And ensembles are sort of by definition shovel ready when you have one. Any other suggestions? Would the same apply perhaps to our coupled interactive ice sheet simulations with Greenland, where we'd like more than one realization? Any thoughts on that, Miren, if you're still on the line? It's getting late in Europe, so I'm not sure folks are still on. How about if we move on to the discussion of model diagnostics? Kate and Gunther, if you'd like to join in, would you like to moderate the next few minutes and take suggestions for land ice diagnostics that people would like to see?
Sure. I've got a slide where I was starting some notes here, so I'm going to share my screen again real quick. I hope you guys can see this. So I just wanted to mention, goodness, my hair at this point. Sorry, some broad outlines from the previous year's discussions. So our initial goals were that we wanted this package to integrate with the CESM post-processing package closely. And that is built on Python. And since it's outside of a regular CESM run, it happens offline. It actually has a lot of access to a wider range of Python packages than CESM itself does, which is useful for plotting and post-processing. However, the software engineers that were responsible for maintaining this package have both basically moved on from this project. One is retired and another is doing other things. So I'm not sure how much longer this post-processing package is going to be supported in its current form. I think it's still a goal to aim for this, but there's been a lot of diagnostic works in NCAR using the Pangea libraries recently. And some scientists have felt that there's better ways forward with that particular Python package. So if anybody has thoughts on which Python we should aim for, that would be useful for me as well. Another one of our goals was to make it, relative to other processing packages, easy to add new diagnostics. We don't necessarily want it to be something where anybody can just throw something in there. We do want to make sure that the diagnostics that we add are scientifically useful and validated to be what you would expect them to be. If you are computing a field, that you want to make sure that it's computed the way that you would expect it to be. But we also want to be able to update older diagnostics over time as the model changes and new information comes around. And again, we also want to integrate with the diagnostics and observational data sets and online repositories like GHub or other places where observational data sets are available that would be useful for comparisons. So if anybody else has other thoughts, I can take some notes here, and I'd be very interested in hearing what people think. Ooh, hello.
And I would like to add to this, when you think about CESM diagnostic package, it could be for future run, but also we need also a lot of insight on how to make it useful for paleo run, because sometimes the needs are very different of what we'd like to plot. So if paleo folks have any needs or ideas, please speak up. And Heiko, you have your hand raised.
Yeah, I'm still awake. Just one comment or idea. Like in my own experience, I think there's really good use for a package that is kind of very general, produces a certain set of diagnostics that are consistent between different runs. So one kind of standardized package. But I think there's also a lot of need for a more direct, quick way of looking at diagnostics. And so I was wondering if there's a call for kind of separating this in two different efforts, like one that really looks at this more standardized Atlas kind of scripts that run or that everybody can run and looks basically the same for everybody. And then something which is more specific and maybe more quick to turn around, that you can just shoot off and have some quick ideas of what's going on.
I would say at NCAR, typically those quicker diagnostics are handled by the scientists and often very specific to the experiment that they're working on currently. I'm not sure how to best approach a question like that. It might be able to subset. So if we had a large standardized set of general diagnostics, and then if you only wanted to run like 2 or 3 specific ones quickly, that should be relatively easy to handle. Does that make sense? Would that be useful?
Maybe just to iterate on this point, like I think it's really great to have a set of diagnostics that are really the same, because then people that produce runs can run it, and then you can compare yours to another run. And so I think it's good if there's kind of like a standard that is the same for everybody, and then there's something that you can configure to yourself, to your own needs, and look into things that you're specifically interested.
Okay. That makes sense.
Oh, did you call me, Gunther?
Yes.
Okay, I'm not going to leave my video off because I'm eating lunch right now. But yeah, just following up on what Heiko just said in terms of the smaller subset. You know, I usually, for now, use NCView on star.CESM.H star, but that's not always the best, especially because the ice grid is different than a lawn grid. But we might inquire of other groups. For example, I know Dan Marsh at a WACM meeting was showing just some quick look Python diagnostics he was using as the model was running, so that he could think about parameter settings or that. So there may be some Python type, and I'm not good at Python, I admit, I'm trying to learn it, but people could contribute that, like Dan did for the WACM group, to just look at the models running.
It says Dan White?
Dan Marsh.
Oh, Dan Marsh.
Who's now in CGD, so.
Yeah. Yeah, there's been a push from Matt Long and other CGD scientists to develop sort of innovative and interesting new Python based diagnostic packages, but it hasn't been rolled into anything, I would say, useful for people outside of their groups just yet. But that doesn't mean that we can't, you know, meet with them and talk about what they've done and what they think would be portable, or a good starting point for us as well.
And to follow up on this, when we started discussing with Matt Long about this, we had in mind that it would be actually quite useful if at least the infrastructure and how you run the diagnostic would be similar from model to model, so you don't have to learn something new for all the different CSM components. So we'll talk more with them and see how we can make this happen.
And maybe even just to say one more thing, because they've all left, but maybe some of the Delft group have already thought about this, that they run the CESM quite a bit.
Yeah. Yeah, they were very interested 2 years ago. We had some sub meetings outside of the in-person winter meeting, and input from the Delft scientists was very helpful. So I would love to hear more from them in their current state 2 years later, what their thoughts are. Any other, am I missing anything from the chat? I don't seem to have a chat window when I'm sharing.
I can see, I'm not seeing anybody raising their hands. So typically when we start working on diagnostics, it's very useful to design a package. So I had in mind for some time to start a CESM package for Python, where we can actually centralize the main function that we are all using, and we all have a version of somewhere on our desktop. And so as I'm studying this, and hopefully it would be useful for the rest of the community, it would be great for me to know what the community the function that they typically use for analyze the results so that it could be available to everybody, and they would just need to download this package and just find the function that they always use to be there.
That would probably be useful in a lot of ways, because it means that there'd be less work for people to set up our diagnostic package later if they already have a current set of libraries that they like to use.
Exactly.
Or installed, yeah. Python, one of the problems with it is this like plethora of supportive libraries that some do very similar things, some get long-term support, some don't, and it can be difficult to manage all of these packages on your own. So having a standardized set would definitely be super useful, I think. I agree.
Kate, was the project you're talking about with Matt Long, is that the GeoCat project? Because I'm wondering if there's any overlap between that GeoCat project and diagnostics for CESM, because it's supposed to be aimed at doing what NCL had provided, which is something that is very easy to use with CESM.
I'm not straight up familiar with the term GeoCat. I have heard of the PanGeo project, which also has this geo word in it. I don't know what specific results or tools have been developed from that. It could very well be exactly what we're looking for.
But I know there's a
I'm not personally familiar with that.
A team of people in the basement, i.e. Sizzle, who are working on it. So I definitely know it exists. I just don't know if it's what Matt Long is working on.
Yeah. Okay. So you're saying it's an NCL type.
Well, it's Python based.
Yeah.
It's a Python library that's supposed to reproduce sort of what NCL had provided the community.
Okay. To create.
Heiko, go ahead.
So I don't know if anybody remembers it, but Joseph Kennedy, during ISMIP 6, he worked on a set of scripts that would produce something like a standard atlas of ice sheet model output. And this was part of a larger set of tools that they developed for ice sheet evaluation and verification. I forgot the name of that, but so LiveKit, voila. So that may be something to hook up to.
Yes. Yeah, we actually have LiveKit at NCAR. I know Bill Lipscomb sees it a bit. From what I've heard, the learning curve can be a bit high for that. And it isn't currently integrated with the post-processing system that we have.
I do have trouble running LiveKit, so if it could be made easier, that would be music to my ears. I currently just kind of hack it. So it's definitely not suitable for a hack. Yeah.
I'm going to talk to Adam about how to hack it.
Okay.
I'll just add this. Talk to Adam about issues.
Let's bring Joe into that conversation too.
Yeah, for sure.
But I expect he'd be glad to help if he has the time.
Yeah.
And I personally see LiveKit as a different set of tools. Like the way we use LiveKit is like LiveKit has a potential to run CESM simulations that you preset and to compare your code. Like a new release, for instance, you could create it with like it would run it and compare it to other piece of code. Mm-hmm. And so that's something also different compared to like just a diagnostic where you just want to see a set of plot for the result of your simulation.
That makes sense. Another one of the questions that I kind of had here, the current CESM post-processing tools include some data manipulation tools like averaging over certain time periods or producing time series data instead of time slice data, which is what comes out of the model currently as default. I'm not sure if Heiko's hand went up before I brought this up, so maybe we'll switch topics back and forth a bit. But one of the things that we may want to think about is how we most want to visualize our variables. Do we want to focus more on a time series? Because that does seem to be what I see mostly from scientific presentation series, a lot of time series. Or are people mostly interested in sort of two-dimensional fields averaged over time? Or do we want to have even balance? Things along those lines would be a question. Because it does require some data manipulation on the back end going forward. Sorry, Heiko, I hope I didn't just talk over you.
No, this was a hand that was still up from before.
Oh, okay, good.
No worries.
All right, fine.
But I can comment on this question of time series. So I think with many fields, in terms of geometry, ice sheet geometry, it's not really necessary to average, because the snapshots is actually what you want in a 2D sense, or snapshots of 2D data. Then there's also a bunch of interesting scalar variables that you want to have as time development, ice mass above flotation, integrated SMB, mean bedrock elevation if you have it changing, this kind of stuff. So I kind of see it as a combination of more like line plots that have like these classic compounded variables, if you want, integrated values, and then 2D plots for specific time periods.
Okay. Yeah.
And that's probably more interesting to have the possibility to have several time slices for the beginning of the experiment versus the end, or every 50 years or something like that, rather than averages over a longer time.
Okay.
For the 2D.
Before I just wanted to follow up on this. Yesterday, in some talks, yesterday we saw that there are an analysis to analyze different, like right now the CESM output give you a global global scalars, but it looks like there could be some interest in getting some scalars regionally. Is there some?
So you would almost specify like
by basin, for instance. Right.
Yeah, regions. That is harder.
Like right now, for instance, like if you give the INBI basin map, or like, I think it could be interesting to be able to output the scalars per basin. And so we can do all of this post-processing given CESM variables, but.
Yeah, but usually that's the kind of thing that, again, it's not done as part of a large scale package. That's more of a specific to an experiment. But it's also the kind of thing that a lot of people do with their experiments. So, maybe there's a mechanism that could be provided for it rather than a specific thing. Specific regions, as I would say. Sorry, Betty, why don't you go ahead?
So yeah, just following up again on Heiko. I really, for paleo, we want time series are good. We usually want those, but we do want averages. You might want to do like a 30-year average or something around a specific time period. Even if you're looking at future, you might want to do 20 years around time of doubling. So I think some averaging is also good for 2D plots. An example is the land model working group. Allows you in their diagnostics to both do some averages, but then some time series. And they actually, I think because we asked for it, have, for the 2D plots at least, I can't recall the time series, they kind of zoom in on Greenland for us, and also possibly Antarctica, but I know for sure on Greenland. So
yeah,
having 2D average plots would also be good.
Yeah. So 2D averages. The averages. The current land model working group diagnostics package has a subsection specific to Greenland that Jan Linnertz actually, I believe, or somebody working with him. Am I right, Bill? You look like you're going to jump in there. Okay. He wrote those about, I've heard, possibly more than 10 years ago. I personally have had trouble getting those to work. It's just the land model diagnostics package in its current form is very fragile in my experience. So I agree that would be a great list of diagnostics to look at and replicate, but I don't find it to be a particularly useful tool for development as it currently is. But yeah, absolutely.
Yeah, be more production type things.
Right.
Development.
Sounds like a good diagnostics package is basically a holy grail, something that we desperately want, but we can't seem to achieve. Because, Kate, I think you've critiqued every single diagnostic package at NCAR so far as being bought. And I agree with you. And we're trying to make a AMWG diagnostics package that's no one can make fun of, and it's difficult.
I didn't mean to make fun of it. I hope it didn't come off as dismissive.
No, it's okay. I get the point. It makes sense. I just want to make it clear that this is very difficult.
Absolutely.
There's a lot of interests.
So, Kate, what do you think of the climate variability diagnostic package?
I haven't used the climate variability diagnostic package. I've used the atmospheric model variability diagnostic package, and I felt that was similar enough to the atmospheric model working group diagnostics that it was very usable. But again, it was based on NCL and C shell scripts, which hopefully we can move away from in the future.
There's a remark from Samar in the chat, and she said, I agree long-term averages, climatology, that annual and season monthly scales for both line and spatial plots are helpful. And I just wanted to be to have some precision. Do you also mean this about those averages for land ice output?
Good job. I'm sorry, I did not understand quite what you were saying there. Can I find this chat?
Yes. So what it was posted to me.
I see.
She's saying that she agrees that seasonal and monthly averages could be useful. And so my second question here is, are those field useful, like in terms of ice thickness, like what the typical land ice output would be, or is it more like what you expect from CLM output? Because there's a difference, because CESM gets, in a couple of simulations, CESM gets surface mass balance information from CLM. And it's
sorry,
the same grid.
Sorry, I actually only sent that message to Gunter, but what I was thinking of more related to CLM, so climate forcings, long-term averages at seasonal or monthly timescales.
Yeah. That should be covered by, I would say, other diagnostic packages. It probably wouldn't be specific to the land ice, but I could see how having instructions for creating those would be very useful to land ice working group members. So it would definitely be part of a documentation process, I think, at that point. Does that make sense?
But I would add, you might want these from the land ice also. You might want to know, I guess it's called in your output ARTM, temperature at the top of the firn layer. It might be interesting to see a monthly type, how it changes in the summer or that. So there is some CESM output that might be useful on the monthly or the seasonal.
Well, CESM by default produces your yearly history files, right, Gunter? So
that's right.
Is there seasonal information within those, or is it mostly your averages? Not so much. Okay.
You would have to change the output.
You would have to change the output to support it.
I talked about maybe having more than annual averages, but that would be a development in CESM also.
Yeah.
So this comes out, I think that there was a point of discussion here that we could downscale the CLM data at the CLM frequency, which is more frequent than. So we can have the coupling history files from CLN at a higher frequency, and it would be great to have like some sort of post-processing downscaling program that can just downscale this data to the CESM grid to do just these averaging processes that Betty is talking about. And now we can ask the question whether this downscaling process should go into this diagnostic package, or if this becomes a bit too much.
Yeah, that could be a bit of a stretch, especially since this is something that's handled in the coupler right now. It might actually be better to talk to Bill Sachs about this, about adding it as a coupler history file instead of trying to do it offline. Because I feel like if you try to replicate something offline that's being done in the model, instead of just looking at what's being done in the model, you have a chance to diverge from the code. I know the coupler doesn't change very often, but if we don't exactly replicate what the coupler is doing, then we may not be actually looking at what we think we are. When we could just produce the output from the coupler that's already downscaled, and we can see exactly what's going on.
I see the tension in this both ways. I'm not sure what the right answer here is. The problem with doing it, I completely see your point, Kate. I think you're absolutely right. On the other hand, the way things are now is needing to specify CESM grid ahead of time, and in fact, running with CESM just for the sake of having this downscaled output, and that's not. I feel like this has caused a lot of issues with CESM2, is the need to have CESM in place just for the sake of having this downscaled, these downscaled forcing. So I think we maybe need to think about some in-between solution, whether that's, maybe we still specify a grid, but do it in a way that we don't actually need the whole CESM model there just to downscale. Or if we can have the routines that do the downscaling that be more modular so that they can be built either within CESM or from a standalone tool, though that's easier said than done.
Yeah, okay. I was like, that's a good idea. Oh, you're probably right.
I agree with you, Bill, about the value of having a tool that will downscale onto someone's grid, which wasn't used in the CESM run that generated the data you want to downscale. I think it can be the setup we have now is pretty limiting if you're not interested in the standard existing grids.
So I think if there's enough interest, if there's going to be true value in doing kind of arbitrary downscaling to a grid that wasn't even envisioned at the time of the run, then I think that maybe that rewrite for making those routines more modular might be worth the effort. But I don't know, we'd have to look at that.
So just officially, it's way past noon, so we can keep the discussion going as long as people are willing to stay and talk, of course. But if you need to go, feel free to go, of course. Yeah, Heiko, go ahead.
This was mentioned earlier on the talk, on the call today, that Leo has developed this downscaling scripts that you can use to extract data even if you're not running CESM. Is everybody aware of that? Because I also use that basically what you have to do is set some flags in the coupler to write some additional files, and so you don't even have to do a no evolve to be able to extract that data. But the format it comes out is in some kind of weird column format, so there's kind of like several processing steps to get this out of the coupler done. But it is possible to do it without running CESM. So
yeah, so what you can get out of, I mean, I think what you're referring to is what I've kind of helped put in at one point was the ability to, you can get the fields that are sent from CLM to the coupler, so per elevation class. And then the question is, okay, how do you get those onto a CESM grid, right? So, I mean, well, one thing you can do is just run CESM with those fields and with a T comp set, so a CESM only comp set, and just let CESM run and downscale it, and maybe that's the maybe that's your tool there. Alternatively, you need to do something else offline to downscale those fields, right? I mean, Heiko, am I understanding what you're saying correctly, or am I missing something there?
No, yeah, I don't know ultimately where the origin of these scripts comes from. I just had it from Leo. But my point was that you don't have to run CESM in order to reproduce SMB, for instance, or the temperature on any topography that you want. You just have to make changes in the CLM and the coupler.
So your point being that Leo has some scripts to downscale those files once you have them to the CESM grid. Yeah. And then I think it just comes back to Kate's point, which is, well, is that downscaling method exactly the same as what you would get in CESM? It's probably about the same and conceptually the same, but whether it's exactly using the same downscaling algorithms may not be. And so if that's whether that's important or not, depends.
Yeah, in my understanding, it was at least very nearly the same. But I don't know about the details of this. Mm-hmm. Yeah, but this is a point, of course, that this is the place where you want, where I see the need for averaging, because you may want to have an average SMB over 30 years or something like this. I think on the ice sheet side itself, you're probably good with snapshots for most of the variables, but on the forcing side, you may very well be interested in longer period averages.
We found that, so this was a problem in the for these TG runs that Michele was doing for this study. We didn't want to generate a lot of output, right? So we were generating a CESM output every 100 years or every 500 years. And then the problem was that the SMB was instantaneous from 1 year, and you want to sample a climatology. You want 30-year mean of the SMB. But then you can ask CESM to produce output that is an average flux over a certain period of time. So what Michele was presenting here, where all the time when he was doing these videos and so, it was 30-year SMB, 30-year mean all the time, not instantaneous. But this is not a problem with that. This is not that you need some diagnostics. You could directly prescribe that in CESM, deciding which kind of output you want to have, whether it is instantaneous, because there are you can switch between instantaneous SMB or a flux over 30 years, 20 years or so. So this is easy to fix, let's say. Okay. And coming back to the scripts from Leo, so I think you were discussing two different things, Bill Sachs and you, because Leo was using CLM output at different elevation classes for all the SMB components or even energy balance component, and at different elevation classes, and then you can then map it to whatever topography you want. But this is about SMB components. While I think what CESM is gonna get is not these individual components, it's only getting the SMB, the integrated SMB. And then there was this other problem, whether with the coupler files you could plot certain things. For instance, because I would be interested in these things, for instance, would be from the coupler, not components. No? So from the SMB, finding out what is the equilibrium line altitude, or obtaining profiles of the SMB with elevation. No? That would be very interesting in this when you have an evolving ice sheet. So how the SMB is evolving with the topography, or when you translate the force into a different topography, and so on. So something that, yeah.
Okay.
Yeah. Yes.
So some of that is just related to history changes in general. So maybe more history output from the coupler, and then documentation on how to handle a history output from CESM to get different options for what you want. Not necessarily actual tools, but information about how to get different sorts of history out of CESM. Would that be helpful for you or your group, Miren?
I didn't understand what you said.
Yeah, oh, sorry. So sort of sound to me like what you're describing now is just getting different types of history out of the model that's there currently. And that would be more of a documentation question and less of a tool. Would you guys find it useful to have better documentation on how to get different types of history output from the model?
No, I think we found out for this instantaneous, and no, what I was actually asking, it was around, I was saying that it would be indeed very interesting to have information or diagnostics of how the SMB changes with elevation.
Okay.
Yeah, that is something that you get from the coupler, not from the history files of CESM.
I see. Interesting. Okay. That's
it was just
can of worms right there.
yeah, I was adding that I was also interested in this.
Okay.
Obtaining more information from the coupler files.
Okay.
I'll just add, I mean, in case Kate, this helps with, designing how to get the diagnostics, that I think those same diagnostics are available from the CLM output if you set it up, if you request the right fields on there. Sometimes that can be, typically we don't use the coupler history files in diagnostics packages. So
yeah, it's very true.
So you can use the CLM ones instead.
Okay. 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 That's a lot, you guys. Thank you so much. Are we starting to wind down?
I believe so, slowly but surely.
Down to 11 participants.
Ah, okay.
Including a very brave few participants like Miren in Europe.
Yeah, absolutely. Thank you for saying that, Miren.
A couple in Michigan.
I'm going to make that 10 now. So
right.
Thanks for the great call.
Thank you.
Thanks very much for joining us, Heiko.
Bye.
See you later.
Thank you, Heiko. I think we have a lot of information to have to occupy us for quite a while.
Yeah, I agree with Adam. We probably designed the most impossible diagnostics package ever at this point. But it's it's good to have something to aim for, even if it's not exactly what comes out of the box at the end.
Yeah, but anyway, so when you go with a list of wishes, then the list can be infinite. But for me, the bottom line is that having something is infinitely better than having nothing, right? If you make the ratio, it's infinite. So starting with something, that's great. That's great. No, so I can say, it would be great if we have this and that. But if it is not there, having the zero order package is fantastic. It's already fantastic. Something to start with, and that is common for everybody. That's great.
Did you say sea level package?
Zero order. I mean,
zero order. Okay.
Yeah, a very basic, package with a couple of things is already super good. That we have a basis to be done.
Great. That's awesome.
And having some dedicated funding for Kate to work on this is great too.
Absolutely. Yeah, it's definitely gonna help. Okay. I'm gonna stop sharing my screen because I don't think you guys need to note so much. Okay. Well, thank you. I'm cool with calling it a day now.
Thank you, Kate. Everybody.
Yeah. All right. Yeah. And again, most of the rest of you here know my email address. If you have any other thoughts or things that come up later, feel free to shoot me a line.
And then the paleo session, joint paleo land ice session starts tomorrow, I believe at 9. And I'll have to check the link, but I don't think it's the same as today's link. It might be yesterday.
It's the same as yesterday.
Oh, okay. It's good to know. Are you sure? Because I have like 2 different links for yesterday too. I'm sorry, I'm a little confused. Maybe Stephanie can send out an email with the specific links for tomorrow. It looks like she's.
I can ask Elizabeth.
Okay, thank you. It would be super helpful because I have gotten confused over the last 2 days.
Hey, Stephanie, is it possible to save the chat messages?
Yes. Let's see.
Or is it something we need to do? Or
we're recording. I don't know if we're recording. Let's see.
You just go and you open the chat and you say there's a little 3 dots and you just say save chat.
Got it.
Oh, that's better than control.
Thank you for reminding me. Okay, so the chat is saved. I'm going to stop the recording and the YouTube live stream.
And so the recording for this is going to be